Welcome to APEC. It's September 2nd, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. Today, Mark Calvo will present the CBU Quantum Graviton Paper. Tammy Padina will discuss interstellar propulsion, and John Brandenburg will discuss GEM theory and applications for advanced space propulsion. We'll also be hearing updates from our lab partners and finishing off the event with an open discussion by conference attendees. So some quick updates before we get started. Today's event uses StreamYard, broadcasting through the Alt Propulsion YouTube channel. If you haven't subscribed, please do so now. You can ask questions using the live chat feature on the right-hand side of the page, and we will ask them to our presenters depending on time constraints. You can always also view conference replays, details, and speaker info on our website at www.altpropulsion.com. Also, while you are there, please register for our email mailing list. Again, that's at altpropulsion.com. Okay, so without any further ado, I want to set up our first presentation here. What causes gravity? Sir Isaac Newton discovered and expressed gravity in his equations as a force that's instantaneous and of infinite range, while Einstein redefined it as a force resulting from the curvature of space-time limited by the speed of light. Since then, modern physicists have searched for the graviton mass as a less spin 2 particle, but that has been fruitless. Could they be looking for a particle that doesn't exist? Mark D. Calvo will present a detailed model describing the graviton as a shadow force. So I'm going to bring Mark in now. Mark, welcome, sir.
Thank you, Tim, and greetings to all. Again, my name is Mark Calvo, author of the Cosmological Balanced Universe.
Wonderful. And so, Mark, I am going to, I'll disappear and take it away, sir.
All right. Thank you, Tim. In case you missed it, on Saturday, July 22nd, 2023, I gave a presentation introducing a simple galactic orbital period equation that's based on a 9-dimensional quantum gravity influence on the rotation velocity of a large galaxy. In finding that GOP equation, I realized that the gravity constant G held the key, as it represents the vacuum pressure exerted by Hagratian particles in the fabric of space. It's also known as ether, on ordinary gravity matter objects and anti-gravity antimatter objects, as well as it influences the attraction between like matter and like antimatter objects. Space itself sees matter and antimatter objects as voids, and in trying to occupy and fill that area forms a curvature around the objects. That's the curvature Einstein talks about. So in order for me to solve the 9-dimensional galactic orbital period equation, 10 dimensions with time, I had to set aside Einstein's GR equation and Newton's equation and abandon the complex attempts by astrophysicists using modified Newtonian dynamics, or MOND, and estimated dark matter mass effect on gravity within the galaxy. The reason they couldn't find the ether on experiments is because the ether moves with the objects, so it causes the objects to rotate, like the planet Earth. But rather than talk about my entire book, I'll concentrate on the section containing the quantum graviton paper. Physicists have pondered these questions for years in their quest to understand gravity, and yet failed to unify Einstein GR, general relativity, with quantum mechanics into the quantum gravity. I approached this problem with the same method I did for the galactic orbital equation. I took a step back, analyzed observations, and set aside complex equations, and simplified things in order to find the truth hidden behind competing gravity theories, and came up with a simple solution to quantum gravity. I called that solution the quantum gravity paper. To put my method into perspective, imagine for a moment that there were two young sailors who each set out on a journey due east across the Atlantic Ocean from Lewes, Delaware to Lisboa, Portugal, in their newly inherited motorized yacht with nothing but the aid of a magnetic compass for one and the use of the star constellations for the other. Both were convinced that following that one eastward geodesic line would get them there. However, upon reaching the completion of their journey, ended up at the coastline of Western Sahara of Africa. Both sailors' 3D method across the Atlantic failed them because they did not account for the 3D movement of the ocean currents and the 3D influence of the atmospheric winds. Here I'm referring to the ocean currents as space and the atmospheric winds as anti-gravity influence. This is the 9-dimensional quantum mechanism for understanding what causes gravity in both the micro world and the macro universe. Most important of all these assumptions is that all matter consists of 4 elementary standing wave point particles: positive, negative, neutral, and anti-neutral. Neutral is sometimes referred to as neutrino and anti-neutrino. And that these stationary standing waves have decreasing intensities which extend outward in all directions toward infinity. And that their force per Coulomb law inversely proportional to the distances between them. And that any acceleration or vector changes of moving point particles generates positive mass and or negative mass, depending on which direction and what is causing the change, which in turn affects gravity and or anti-gravity forces. These 4 basic point particles are essentially massless when traveling in straight lines at a constant velocity. Scientists have recently discovered that the differences between the strong nuclear force and the weak nuclear force is about 100 to 1. This is quite interesting for the quantum realm. But how does that apply to the macro world? According to Einstein's acceleration gravity equivalence principle, an astronaut aboard a rocket thrusting upward and away with sufficient acceleration from the Earth's surface to 10 kilometers could experience 100 Gs on his body. But then at that altitude, when the engines fail him, his rocket free falls back to Earth. He experiences 0 Gs until the rocket drops to 5 kilometers, at which time the engines reignite and send him back upward with renewed acceleration to 10 kilometers, only to repeat again. This up and down oscillating acceleration motion generates the gravity constant G. In the first line, with R equals 5,000 meters and the upward acceleration of 972 meters per second squared, we get the time of 3.2 seconds. And with the downward free fall acceleration A of 9.8 meters per second squared, we get the time of 31.9 seconds. And in doing the rest of the math, we see that the rocket's up and down acceleration, oscillating acceleration and free fall motion, which simulates the differences between the strong and nuclear forces, clearly generates the gravity constant G. Since the force of gravity in Newton's equation is fractal by definition, we expect that the more minuscule the masses of M1 and M2 are, the smaller the gravity forces between them, which of course is also inversely proportional to the square of the distances between their centers. This is very similar to Coulomb's law. Specifically, point particles motion patterns generate positive mass or negative mass, which in turn pierces the normal stationary standing wave with a spike, something like a micro wormhole tunnel, if you will, to enable the gravity or anti-gravity effect, which is an entropic connection of both objects' movements. So to visualize this, we need to analyze the role of the four basic point particles in generating the strong and weak nuclear forces and the electrostatic and electromagnetic forces. Simply put, a point particle exists in a 3D as a 3D standing wave exhibiting charge, mass, and energy. And that all matter and antimatter are assembled from these four basic point particles in various configurations and patterns. Again, all point particles are excretions from the nothingness of the deep as mirrored reflections entangle with each other. Specifically, when a positive point particle is created, an exact mirror opposite negative point particle is also generated. Being of opposite charges, these two are electrostatically attracted to each other, collide, and then transition into a neutral and anti-neutral point particles. Likewise, when neutral point particles collide with an anti-neutral point particle, they transition into a positive and negative point particles, only to repeat the transition again. So with a hint of conscientiousness and survivability, charged point particles pair up and bond with neutral point particles to survive. But in doing so, the paired point particles have reduced charge of 1/3 and gain additional energy. The pair gains additional energy to leverage short quantum bursts of the strong and weak nuclear forces. These group mutual pairs, point particles, explain why electrons and positrons are sometimes observed as particles, waves, and or clouds. Here is a possible example of how point particles assemble to form an electron, positron, photon, quark, and antiquark. The top of this chart shows the four basic point particles, and then as you go down the chart, you see various combinations form different particles. Here's another example of possible assemblages for photon, electron, and gluon. The top of the chart shows a top-down view, and the bottom of the chart shows a three-dimensional view of those particles. Shown here is an example of electromagnetic particle wave propagating through space. In this example, the rotating photon disk core generates a magnetic field that catapults the separate electron 1/3 negative charge paired particles forward to merge into a -1 charge, which in turn generates a temporary magnetic field that catapults the photon core forward and causes the electron to fall apart into its component paired point particles. This leapfrog effect keeps the photon moving perpetually through the medium of space. The left image here, the left side of this image is the old science portrayal of an atom. The center image is a hyperbolic structure of an up quark, and the right image are these quarks within a proton. In this example here, an up quark is composed of 16 point particles, 5 positive 3 negative, and 3 neutral point particles, where 5 pairs of neutral and positive point particles are orbit randomly at the 3 pairs of neutral and negative charge point particles at the center axis. In this image, the quark core consists of 3 paired negative anti-neutral point particles, essentially 1/3 each charge each, jiggling about a neutral point particle at the center, essentially forming an electron core, which in turn captures about it in a hyperbolic strong weak nuclear force orbital pattern several paired positive neutral point particles. This is the quantum engine, which employs Tesla, Lorentz, EM, weak, strong nuclear force system. The negative antineutrino pairs taps into the strong nuclear force just enough to prevent its paired antineutrino from contacting the neutrino in the center. This short burst and partially quantum Planck distance is just enough for the center core to have mass and act as a counter recoil mechanism or shock absorber. This recoil mechanism stabilizes the quark and enables the core to move in the direction of the quark's quantum attraction toward a common center of mass between quarks. The neutrino to negative antineutrino counter recoil mechanism and electromagnetic Lorentz force provides 33.33 of the strong nuclear force, which transfers completely to the positive neutrino pair, the right side of the image and the left side. The negative antineutrino, in ejecting the positive neutrino, exerts another 33.333. And the positive neutrino pushing back on the negative antineutrino adds another 33.33, while the electroweak positive negative particle interaction subtracts 1. This gives us a total of 99:1 force ratio. From Nikola Tesla's point of view, the electromagnet weak force plays an important part in catapulting the positive neutrino pair outward. This additional force is known as the Lorentz force, provides that extra boost. The number of positive neutrino pair point particles in this configuration determines whether the quark is an up quark, down quark, or neutral quark. Now, let's take the rocket oscillation, which was based on the differences between the strong and weak nuclear forces, into the quantum realm. In the quantum realm, an electron and positron electrostatic attraction and repulsion are basically null at Planck distances. This unique property of stationary standing mass energy waves is what enables the quark's core to form from essentially an electron tightly orbited in a hyperbolic pattern by a positron plus. In the quantum realm, the constituents of the electron and the positron particle are still able to attract and repel as expected, but these short bursts of force is known as the strong and weak nuclear forces. And such resulting hyperbolic pattern enables the gravity effect and its constant G. Superstring theorists coined this pattern as the Caleb-Young manifold. On calculating the inward and outward acceleration times and applying it to figure out the gravitational field generated by the quark's hyperbolic oscillation, we find that it too is also equal to the gravity constant G. But that doesn't define how the two quarks are attracted to each other. To understand the quantum gravity effect between two quarks, we need to realize that each outward hyperbolic vector punches a spike, a micro wormhole tunnel of infinite length, to form an instantaneous entangled connection as two quarks pointers align with each other. In other words, gravity is an effect resulting from the pattern motions of paired point particles generated by the other three natural forces working together. The gravity effect is essentially one of electrostatic attraction. Overall, all the atoms in a given object in space, when combined, balance out to zero charge. But that's not true at the quantum level. When all the quark hyperbolic vectors of two objects align with each other, all their quark core negative charges are then attracted and moved toward these objects' center of mass, which has a combined sum of all the quark positive charges from both objects. To visualize this at the quantum level, imagine two hydrogen atoms in the vast emptiness of space, each with zero charge, one electron and one proton. Here, the three quark pointers in each proton project the center of mass of positive 6 charge, in which the negative 3 charges of their quark cores are attracted toward. Once the electron shells bond, their combined negative 2 charges, negative 6 1/3 charges, form a barrier which limits the quarks from further quantum gravity attraction. Incidentally, the electron shell barrier is a cloud everywhere else except where the bond is, and that's where it becomes negative 2. And then that electron shell barrier breaks down by immense gravity pressures in stars, particularly in neutron star and denser objects like the black hole. Using quarks as the smallest quantum gravity particle, we can easily determine that the black hole must therefore be an oblate sphere with a calculable radius. This is the 3D quantum solution, which almost explains why gravity is considered to operate instantaneously and of infinite range. Here is a detailed example of calculations showing how the vacuum pressure from space is detected as the gravitational constant G. G is the blue line that's highlighted on the table. The left image shows pressures and cones and spheres, areas, and the measurements are on the right chart on the table. In this example, the M1 is the mass of the sun, and the inner planets, while M2 is the mass of Jupiter. So according to Newton, the two objects are attracted toward one another with the force of F equals G M1 M2 divided by R squared. This is true because that path is the vector of least resistance to the vacuum pressure of infinite particles in the fabric of space itself, which suspends both objects, which of course pushes these light matter objects together. So gravity is push and pull working together. In this example, we see three-dimensional attraction of matter objects toward each other, and another group of 3D effect of space pushing matter objects together. In this is 6D of the 9-dimensional interaction of matter, space, and antimatter. The other 3 dimensions effect is from anti-gravity, antimatter pushing on objects. Space views the presence of matter, objects as voids needing to be occupied and filled, and in doing so form a curvature around it. While matter, on the other hand, sees space as a void and tries to disperse to occupy it. That gravity struggle between space and matter typically forms it into a spherical object. Incidentally, the names of the 2 sailors who followed the geodesic line to sail across the Atlantic could have been Newton, who alluded to the gravity mechanism, or Einstein, who defined curvature but ignored the ocean currents of space and the push winds generated by anti-gravity and antimatter. That's the 9-dimensional universe. This image shows the push and pull of 9-dimensional gravity, anti-gravity forces within space. In summary, the quantum graviton effect is a 9-dimensional mechanism applicable to the micro and macro universe. Ordinary gravity matter attracts other ordinary gravity matter in 3-dimensional space as defined by Newton's equation, while the 3-dimensional ocean or fabric of space suspends, rotates, and moves ordinary matter objects within it, while another 3-dimensional of anti-gravity, antimatter repels or pushes like the wind on the same ordinary gravity matter objects. This is the 9-dimensional quantum gravity mechanism of the micro world and simultaneously the mechanism for the gravity of the macro universe that Newton could not define within Mathematica Principica. So he wrote his document as a philosophical solution. I took the same particles, the 4 particles, and I tested them within the fusion structures of stars, particularly our sun, and it perfectly aligns with science's interpretation of how fusion works within the sun. And that concludes my presentation. And this is the cosmological balanced universe, CBU, a unified theory. And shown on this chart is the 2 sides of the universe and how each side replenishes the other. Tim, that concludes the presentation.
Okay, sorry about that, Mark. Yeah, I heard you say that, and then you put the additional slide up, and it looks like you have some backup slides too. So,
Yeah,
we've got about half an hour left. We could do Q&A. I would love to do Q&A. We have questions in chat, and then if you want to run through the backup slides, that's also totally cool. So
okay, we can. I'll bring up the backup slides and show.
Yeah, I would just say run through some more details. Thank you so much. Thank you so much. And then when you do that, we have to clap for you because that's an awesome presentation.
All right, let me go through the backup slides then.
Okay.
As I said earlier during the presentation, the radius of the black hole can be determined simply by using the quark sphere particle as the source of gravity. And on this chart here, if you take the mass of the Earth and the radius of the Earth at 6.63 meters, you can see it on there. You can compress the radius of the Earth down to 0.00887 meters. That's the size of the event horizon around the Earth black hole, if you made it into a black hole. And the radius of the black hole surface would actually be 0.00006 meters. So the same thing with the mass of Jupiter. If you take Jupiter and compress down into a black hole, you would get a black hole event horizon at 2.82 meters. And the surface of the black hole, which I'm talking about, the quark surface, would be 0.0181 meters. And if you took the sun and you tried to compress that down into a black hole, the event horizon would be 2.953 meters. And the surface of the black hole would be 18.9 meters. And if you took Betelgeuse and you compressed that down into a black hole, the event horizon around, I guess it's understood, the event horizons where light cannot escape is going to be 22,720 meters. And the black hole surface would be around 145 meters. And if you took the center black hole in the Milky Way, Sagittarius A, the black hole event horizon is quite large. If you can look at that, 12 billion. And the surface, the radius of the black hole is about 77 million. If you took the background, microwave background signal, that is the image that shows the invisible part of our universe. Each of those bubbles on the WMAP or Planck 2017 chart each bubble represents the halo around the anti-gravity, antimatter galaxies. The halo is the outer shell where matter is spewed out from the center of the galaxy. And the image on the right there shows a simulation of what each of those galaxies, the position of each of those galaxies would be. Now, I alluded to anti-gravity, antimatter galaxies spewing out matter at the halo of their galaxies. And they do that because in the center black hole, the supermassive black hole of the galaxy, they have the ability to crush down and transition anti-gravity, antimatter into ordinary matter particles. In other words, they compress the antimatter, anti-quark down into almost nothing. And in order to survive, it flips the particles within the structure and causes it to become a quark particle, a neutral quark particle, which floats to the surface of the black hole and gets ejected out into space. And that grouping travels in a wormhole tunnel. If you look at the centerpiece on this chart here, that's the black hole orb that gets ejected from the anti-gravity, antimatter black hole, white hole to us, but black hole to that universe. And around it is a wormhole tunnel. And that wormhole tunnel is represented by a square root of 2 in equations. And the gravitational waves around the wormhole tunnel hold electrons in place in the center. And the eddies of electrons orbit around the black hole orb until the tunnel collapses at the exit, at the halo of the anti-gravity galaxies. When that tunnel collapses, those eddies are released. Eddies of electrons are released as a microwave burst of exactly what CMB radiation detects. And this is the summary of the galactic orbital period rotational velocity. It's a simple equation. The first part of the equation is basically Kepler's law, but modified with Schwarzschild mass put into. In other words, if you took a section of the galaxies, it included everything within that radius. And then it determines at that radius what the orbital speed would be. The second part of the equation is what I call space influence on the galaxy. In other words, the particles of space, which is quantum, pushes on the galaxy. It causes the particles of space have a gravity, anti-gravity pulse. That oscillation rotates the galaxy, kind of like an electric motor, AC current rotating a permanent magnet in the rotor. So it also represents the excretion of anti-gravity from the center of the black hole in the center of our galaxy and all the other galaxies. So the combined effort of those two are incorporated in the second part of the equation. Incidentally, each star has a shield around it. Basically, what that means is the mass of the star, like our sun, forms a shield around the star. And that shield takes the second part and makes it into equal to 1. In other words, it's not there, it's not existent. So within the solar system or within the star system, only the first part is applicable to the rotation of the orbital patterns of the star and the planets. The same is true in intergalactic space. Outside the galaxy, the second part also goes to 1. And that gives us Newton's equations work perfectly between one galaxy attracting another galaxy because there's no rotation involved. It's just one direction. And, in the GOP solution that I gave, it also predicts the mass of the galaxies at each of the sections. It predicts the star's orbital period and its orbital radius, and the star system's radius and its mass. And it all comes out perfectly. These are perfect duplications of velocity curves that the galaxies, extragalactic objects have. Again, this is just a repeat of the same chart, but from a different perspective. And that's the cover of my book, front and back. You can find it on Amazon or Barnes & Nobles.
Wonderful, wonderful. Well, Mark, thank you so much. Here, let me take that down. So let me see. It's just you and me in the studio. So I am going to give you an enormous applause, and everyone who is watching on YouTube. We actually have several hundred people watching on YouTube right now, but I can't put them up on the camera. So they need to applaud as well. Thank you. That was an amazing presentation, incredibly detailed, and you have done so much work on that. So thank you so much. So, I had a couple questions while I was watching that. So when you're describing gravity as a shadow force, I think Lesage gravity was kind of the first attempt at that, like well over a century ago. Is that something that kind of resonates with you, I guess?
I'm not familiar with that theory, that part. What I can say is that if you understood what I was saying, all the quarks centers, they have a line that forms going out. So if an object in space, like the Earth, all the quarks form like a beam of light, if you will, toward an object like the sun. And then the object from the sun forms like a beam of light toward the Earth. And so if you look at the chart that I was showing you where the push comes in, another way to explain this is you take two hot air balloons and you float them over the ocean, and you have a hurricane off in a distance. The hot air balloons are going to be pushing toward the hurricane by the forces the winds going into what's known as a void in the center of the hurricane, the eye. So you have these two hot air balloons pushing toward that eye, but at the same time, they're being pushed toward each other because the pressures around them are pushing things together. So you have a double effect, and that's the same in space. You have two objects in space that are floating. If they were just one object, it'll be just either rotating or stationary, and if it was moving, it'll move basically at a constant speed. But if you have two objects, now you have two objects being pushed together by space pressure, vacuum pressure, if you will. And that vacuum pressure is the gravity constant G. And so Newton captures that that pressure in his equation, and he explains how it works. So he got his solution from Kepler's orbital period equations. And so that's how it works. But if you look at what I just said about the hurricane, the atmosphere sees that void in the center and tries to fill it with pressure, and then it forms a curvature around it, and it's, the spin of the hurricane eye. And then, but if you look at it inside the hurricane eye, it goes upward and out. So basically, the hurricane eye sees space as a void, so it tries to fill it, so it takes its pressure and pushes it out. So that's the same thing that happens in the sun. The sun gases see space around it as a void and tries to spread out, but the space pushes the sun together, and at the same time, the particles in the sun, quarks, pull the particles all together. So you got a double gravity, you got a pull and a push of gravity. That's how you form a sphere. If it's large enough and malleable enough, it becomes a sphere, which is understood as the least, the best form to hold. Okay, just like a bubble, you blow a bubble in the atmosphere and it'll form a sphere.
Yeah. Well, so what you're describing is similar in principle to something called Lesage gravity, although his model was much more primitive, right? This was a very long time ago, and so he didn't have the tools or knowledge that you have today. But so I should also ask, what do you think might come out of this in terms of propulsion applications, if anything?
In the book, I have frequencies described as the frequencies of space, which has an oscillation. If we match the frequencies of space, we can propel spaceships toward that frequency. And I was talking to a CEO of a company that's doing some other work about that, and he's using the Lorentz force to send rockets in space. And if you use the Lorentz force and the same similar description that I had for light or electromagnetic wave, as it pulses through space, you got the core magnet photon, and then you have the pieces of electron circling around it. And as they group together to form a -1 charge, they create an electromagnetic field that pulls the core forward, and then it breaks it apart. Wherever that grouping is, that's the frequency of the EM wave traveling through space. If you take that kind of effect into a spaceship, you can probably push the spaceship with its own energy forward, or you can use the Lorentz force and create a magnetic field that pulses with the oscillation of space particles, Gravitonian particles, I call them. You can call them ether if you like, because that's the common name that everybody understands.
Okay. And AJM in chat, actually, I'm just looking at the chats on the side here. He was like, please explain gravity. So in your model, gravity is basically, again, you've got vacuum pressure, right? You have the virtual particles, the quantum foam, whatever we call it. Now, but there's a little bit of pressure, and then you have a line in between any two objects, any two mass objects that block that, and it pushes them together. And that's gravity.
Right, let's go ahead and talk about the entirety fabric of space. The entirety fabric of space are made up of neutral quarks. These are supersymmetrical neutral quarks. And I say they're supersymmetrical because they oscillate between positive mass and negative mass and positive mass and negative mass, which translates to gravity, anti-gravity, gravity, anti-gravity. And if you take particles that have two gravity attractions toward each other, they will pull toward each other. But once one particle flips over into the anti-gravity, then they push apart. In other words, they have a limit. They cannot come further than that limit. And in my book, I'm estimating that limit to be about 1 meter, 1 quark per meter, cubic meter. And so you have the entirety of space out to, as far as we know, infinite. We don't know exactly what the limit is. But this whole structure is a grid of particles separated by 1 cubic meter of just one particle of hydrogen or ether, if you will. And if you run experiments, you can't really detect them because they're quark size. They're really minuscule particles, but they have enough pressure and force behind them because behind one particle on top of the Earth, you have 1 billion particles behind it pushing on that one particle. So you have the G-force, the gravity constant pushing on the planet Earth. So it becomes a sphere. And then, like I said, if you look at the structure, space pushes two objects together while the space in between the two objects are trying to push it apart, but it's less pressure there.
Okay, so Don Mitchell just put in chat. He was asking, is space otherwise nothingness between the distributed quarks? So you've got the supersymmetric quarks. I think he's asking if there's nothing else in between them or if there's anything else there.
There, in between them could be ordinary matter, or it could be particles of ordinary matter or particles of antimatter in between. Space itself is a special kind of matter. And I call it, I call it a Gaussian because it's a specific space matter, and it sustains itself as a self-contained entity. If you will, the entirety of the universe is basically, someone can conceive it as a bubble, because the outer edge is pulled by the rest of the universe, and it can't go further. So when a galaxy moves toward the outer edge, it'll circle back around and come back in. But we don't know how far that is.
Yeah. No, again, this makes a lot of sense. And, like I think you used the word ether, right? And science is still cranky about that word. But, at the same time, they've redefined etheric models. Again, quantum foam, quantum vacuum. There are so many different ways that the word ether has been redefined and brought back into physics that, in my view, there's really no great way to do it without something in space. Space can't, even though it's empty, it can't be empty, right? So,
right. Tim, one more comment. Space Gaussian particles form the grid first, before when the structure, and I said in the beginning that a positive particle and a negative point particle are created out of the nothingness of the deep. When I said that, I meant zero, absolutely nothing. So now you have a positive and a negative point particle, and quantum mechanics actually supports that. They say when two particles are created, they're entangled. But then these are positive and negative, and they are attracted, and they come back together again and supposedly annihilate, but not in my view. They transition to neutral and anti-neutral. And that's why there's so many neutrinos and anti-neutrinos roaming around in the universe. Until they collide, they will become a positive and a negative point particle. So that's how the structure was created. And the first instinct on the assemblages of particles is to become a neutral quark. That's the first instinct. Same way when creating an atom, which came first, the neutron or the positron? I mean, the neutron or the proton? And you find out when you're building the structure of an atom for point particles, the first thing to come in is a neutron. And so when two neutrons hit and bounce off each other, they exchange particles, and one of them becomes a proton. And then now you can have a positive charge attracting the electrons in space. And basically the cores of quarks are electrons, and orbiting around it is a positron. And then orbiting around that is another electron that forms the atom.
So definitely a complex model. There's a complex model.
Yeah.
And let me see. I think Mark Fiorentino was asking about neutrons. And let me see. Mark was asking about so how would neutrons fit into this? And then someone else was asking about antimatter as well.
Neutrons, as in the particle within an atom.
Yeah.
Like I said, the first thing that is created, if you assemble point particles together, the first thing that comes up after the quarks is a neutron. And what you have, like I said, quarks start out with neutral quarks. And when neutral quarks are attracted gravitationally and hit each other, they exchange particles, and one becomes an up quark and the other one becomes a down quark, which are bonded together electrostatically and gravitationally. So now you have two fields pulling it together to hold it. And then when they're holding together, since you have an off balance now of 1/3 negative and 2/3 positive, you have to compensate with another 1/3 negative. So it attracts another particle. And in that attraction, it forms a neutron. That's the first particle within an atom that forms. And that's how you work it up. And then you work the neutron, and then you have the proton. And then that proton is able to attract a loose electron in space. And electrons are composed of 3 paired particles, if you will. A -1 charge and a neutral charge. And they become a -1/3 charge, but they have the ability to tap into the weak nuclear force. And so when you have these 3 loose particles come together, they come and they spin around each other. And that's the spin that we see in an electron. They come and spin around each other, and then they pull apart. And then they come in again and spin around each other and pull apart. So you see it as a cloud, and then you see it as a particle. And that's how that mechanism works. And so an electron has the capability of gravity field, gravity attraction as well. It has mass.
So Mark, let me put your book back up. Excuse me. Cosmological Balance Trilogy. So the reason I'm putting this back up is where can people get a copy of this? I didn't want to neglect this.
Yeah, the copies can be obtained at Barnes & Noble's website or on Amazon. On Amazon, that's where I first published it, and I call it The Cosmological Universe, a Unified Theory. And then when I went to publish on Barnes & Noble, I called it The Cosmological Balance Trilogy, because when I initially wrote the book, I wrote 3 sections to make it manageable for readers, to about 200 pages each. And then when I consolidated everything, it comes out to around 500 pages. Information in the book, what I just mentioned about the hurricane. A hurricane, believe it or not, is influenced by the gravity field of the Earth. The gravity field of the Earth is not structured stable all the way around. If you take Einstein's simple gravity equation, acceleration equals gravity. So if you follow the trajectory of the Earth around the sun, the orbital pattern, the front edge has more gravity than the back edge of the Earth. So you have a rotational torque on the planet Earth. And these torques actually influence hurricanes. And so another section of my book has how those gravity fields from the moon and the sun influence hurricanes and can spike a hurricane from hurricane category 1 all the way up to category 5 within hours, just simply because it passed over a spike of gravity, anti-gravity on the Earth. If you had an anti-gravity field pushing up on the center of the eye of the Earth, guess what it does to the intensity of the hurricane? It pulls the hurricane tighter in and jumps from category 1 to category 5. It also can loop-the-loop hurricanes. And I plotted all these out with 15 years of data on weather.com. And they all match, and they all explain why these hurricanes acted the way they did. Most weather reporters, when they present something, they scratch their head and say, I don't know how that hurricane changed course. It wasn't supposed to change course. But then I put my equations right over the top of it, and my charts right over the top of it, and it shows why it changed course.
Okay. And sorry, I didn't mean to go quiet there, Mark. I'm actually getting these. What I'm going to do is put these. There we go. Okay. So let me take the book down. We've just got a couple of minutes left. I'm going to remove that one, and then I'm going to share if I can make this work. There we go.
Oh,
so
I
this
gave
is the
my data.
actual Barnes & Noble page.
Yeah, I gave my data to a hurricane hunter at NOAA, and he likes it. He actually wanted me to help. He wanted to help me publish my paper on it, and I haven't gotten back to him on it. So he likes the data. Of course, it was rejected by the Atmospheric Science Journal. They said it's too much against buoyancy theories.
Oops. Okay. Sorry about that. Let me remove that, and then I think I need to add that back in. Oop. No. Sorry, I want to share. I'm being a little slow. There we go. And there's our Amazon page. I absolutely wanted to share that for everybody as well. Again, Mark, my apologies there for being slow. Let me thank you so much for presenting today. You did the earlier presentation for us. Your work is absolutely brilliant. I love what you're doing. We're getting great comments in chat here. It's a little quiet because I think the back to school rush, usually it's kind of a madhouse, but that's good. This lets us focus a little bit more on your work. So again, I will scroll back up to the top. This is on Amazon. So if people are looking for this, let me see if highlighting it works. Yeah, there we go. Cosmological Balance Universe, Triune Dynamic Equilibrium by author Mark D. Calvo. And I want to highlight this. And you had some collaborators as well on that. So Mark, we're at the top of the hour. Let me here. I will take this out. I'm going to bring Tammy in. Tammy can help me clap one more time. Tammy, help me give Mark an enormous applause. Thank you. Mark, thank you so much. I genuinely mean it. It is very intense material to run through. So thank you. Okay. So Tammy, you are up, ma'am, and we do not have a presentation loaded for you. It looks like it lost your presentation. Do you want to reload that?
Yeah. Hold on a second. Should be here. Yeah. Just a moment. Sorry about that. I had to leave.
Oh no, that's okay. It was you did have it loaded.
Reload my browser here.
And okay, there we go.
All right, excellent.
Okay, that was fast.
Okay,
that was fast.
So experiment.
Okay, well,
going interstellar.
Yes, and, but before that,
Thank
let me
you.
let me premise things. So Tammy, I want to show this to people later. I'm going to show them the Hyperdrive Anthropology website that you have put together where you were blogging. Also, I'm going to pester you to share the Clubhouse chats that you have been doing, if you're open to that. Um, so for anyone who's not familiar with Tammy
Absolutely.
Padina, you have been doing absolutely brilliant not just space science, but space science as well as a massive collection of other work in science and technology, futurism, consciousness, the whole 9 yards. And so um, nobody knows this, but I have been begging you, please present at APEC for like 2 months now. So thank you so much. Okay.
You're welcome. And I'm very sorry I had to reschedule, and I'm very happy to be
No,
here today. So thank you
it's
so
fine.
much for
Thank
this
you so
opportunity.
much. Okay. Well, I will remove myself
Thank you.
and thanks again.
So thanks everyone for being here today. This presentation was inspired by my post initially that was entitled Interstellar Propulsion. Well, that was the topic. I've changed a few things. This presentation is just generally an overview. So I love this quote by Octavia Butler. We have only to open our eyes and our hearts to the wonders of the universe, and we will find that we have been living among the stars all along. To me, that means that we just have to look around and we will find what we need in our sense of place for the innovations that we are looking um, to discover in order to solve some of the greatest problems that we have. I do have a video here um, that I would like to share. Oh, just a second. Let me go back. Um, oh, maybe I can't do that, but that's okay. We're going to be covering a lot of material. There's like over 18 slides. Um, so, from fiction to reality, one of the reasons why I say in the post is that we have gone from fiction, science fiction of interstellar space travel just in our imaginations to actually achieving it is because Voyager 1 and 2 are actually in interstellar space. So that was a dream. It's within reach. They will eventually reach the stars. So in this presentation, I'll be going over those various propulsion methods that are being actively worked on: nuclear, ionic, photonic beam propulsion, Alcubierre, and some other theoretical methods. So there is a basic science, right? We are constrained by gravity here on Earth. So getting up there, we have to obey the Newtonian equation of motion, where force applied to mass and the acceleration of the object. So applying that to space travel, we have to use this to calculate the acceleration and velocity of spacecraft. Um, we need the momentum transfer equation in order to figure out uh, just how efficient our propulsion methods are going to be. That brings us to conservation of energy, the actual propulsion methods. If it's using a propellant like we have in rocketry, then we have to pay attention to the initial energy of a system, the work done on the system, and the final energy output to propel the spacecraft. There was this guy named Tsiolkovsky whose experiments contributed greatly to our modern rocketry. And that's this equation here, where we have the impulse. And we're going to be bringing this up a couple of times. So, as far as the efficiency of these different propulsion systems. Um, nuclear propulsion. Okay, NTP, nuclear electric propulsion, nuclear pulse propulsion, they all use nuclear reactor, nuclear device to heat a working fluid, such as a hydrogen propellant, to high temperatures in order to produce thrust. Although it had been proposed in the 50s, it's still limited. There's still a lot of work that needs to be done, and it's still and have to be obedient to the laws of thermodynamics and thermodynamic processes, converting that heat to work. A little bit about Rankine. Okay, so here, N is the efficiency of the Rankine cycle, H1, H2. Those are the enthalpies of the working fluid at the beginning and end of the steam turbine. And H3, H4 are the enthalpies of the working fluid at the beginning and end of the condenser, enthalpy being, the amount of energy in a thermodynamic system. So the efficiency calculated using a Tsiolkovsky equation, which is specific impulse, in a last slide, LSP, being equal to thrust over mass flow rate times the acceleration due to gravity. And that goes hand in hand with the Rankine equation because that's going to be your actual power output. One example of that is current with nuclear propulsion. Back in 2021, NASA had calls for nuclear thermal propulsion projects, and there are currently 3 different companies that I last heard that were working on this, and I'm uncertain because I think it's been a couple years since this page was updated. Which of these designs will be pursued moving forward? But the idea is that in order to test these, we have to be able to have a way to have thermonuclear propulsion that is sustainable. So, legacy and future. So there are nuclear energy powered spacecraft like the Voyager probes that I had mentioned before. Those are now in interstellar, but those use radiothermal isotopes rather than detonation. There are experiments with nuclear fusion, combining nuclei, releasing energy. Back in the 70s, some of you may be familiar with Project Daedalus, which proposed a fusion propulsion interstellar probe using pellets of deuterium and helium-3 mixed together. So the challenges that are facing nuclear propulsion as an interstellar means of travel are sustainability. So sustained long-term nuclear reaction system, overcoming Coulomb repulsion between positively charged nuclei, and being able to contain that reaction over time. Which brings me to the related antimatter experiments. Now, annihilation ratio with antimatter to matter is 1:1. So energy release, that's calculated by energy is equal to mass times the speed of light squared. And so 1 gram of matter to 1 gram of antimatter annihilation yields about 90 petajoules. And that's 21.5 million tons of TNT explosion. That's a lot. That's an incredible amount of energy. The problem being that we don't currently have a way of containing that much antimatter. Antimatter storage is a problem, but there are ongoing experiments. This is a NASA-related design, the positronic drive. Now, positrons are anti-electrons, and they produce gamma rays that provide the energy for thrust. Here, you can see that, let me go here. So the positrons are directed from the storage unit to the attenuating matrix. They interact with the material and release heat. The hydrogen circulates through that matrix, picks up the heat, and then flows through the nozzle. So it's very similar to a plasma drive, as you can see. Okay. And this is just a little snippet I took from Scientific American from a few years ago on antimatter and fusion being used together. It says a fusion-powered spacecraft could reach Jupiter within 4 months, potentially opening up parts of the outer solar system to manned exploration. Okay, a number of hurdles would have to be overcome, particularly in the production and storage of antimatter to make the technology feasible, but some experts imagine could be ready to go in a half century or so. So it's probably not a 40-year technology, but 50, 60, quite possible, something that could have a significant impact on exploration by changing mass power finance calculus when planning, according to Jason Hay, Senior Aerospace Technology Analyst for Towery Group. And that was taken from Future Visions of Human Spaceflight. So antimatter, extremely powerful. It's just a matter of being able to contain those explosions, being able to have enough antimatter, first of all, and then being able to contain those. All right. So radio frequency, photonic, and beam propulsion. So radio frequencies are a type of radiation. So these propulsion systems use radiation pressure that occurs when electromagnetic radiation carries momentum, exerting a force on surfaces it interacts with. That's how we are able to have Wi-Fi and um, different wireless technologies. RF photonic beamed laser propulsion exploits that force at a higher energy to create thrust. It's a lot more concentrated. The frequency range, the millimeter wave frequencies, 30 gigahertz, 300 proposed for RF, can penetrate those space environments and also some types of matter too. It's very efficient. It doesn't require propellant, but these spacecraft are sort of delicate. So a lot of them have to be packed up and then still blasted into space using propellant, right? So in order to get up there, they're still subjected to Tsiolkovsky and momentum transfer equations. So one of these examples, the Breakthrough Starshot project, powered by Earth-based lasers using RF propulsion. That's this one here. And in case you can't read it, I'll tell you the mission highlights. So light, 300 by 300 meters active, photogravitational sail, uses only starlight to navigate between the stars. Capable of visiting 3 stars, Alpha Centauri A, B, and C, the final orbit around Proxima Centauri, and the total travel time is 141 years. So from here, where the sun is, that's the initial sense of energy. And so some of the energy for the propulsion will come from beam lasers initially. But then once it reaches the interstellar space, it's going 4.6% the speed of light. It's going to have to rely on the starlight alone in order to get around these other star systems and make its way to Centauri C. Okay, so the plasma methods, there's a lot of different advantages. It's highly efficient, there's a lot less fuel. It's ideal for those long duration missions. It has the potential to outperform chemical propulsion. And there's those ion thrusters that use electric fields to accelerate those ions in the propellant without needing any kind of explosion necessarily, which may affect the thermodynamic equilibrium. So plasma dynamic thrusters, they use magnetic fields to contain the propellant and accelerate it. And the MPD thrusters achieve even higher exhaust velocities that way. But the challenge is creating and sustaining those fields for thruster operation. So those require a power source, right? So substantial energy requirements. Those spacecraft must generate and store energy for extended missions. Okay, here's the MHD, a basic design concept. So here you can see how this is very similar across different designs that have been encountered. A lot of people in the audience who work in the labs are familiar with this. For laymen, just so I can explain briefly, there in the middle you see the plasma flow. Working backwards from that, the MHD channel is where the magnetic field is controlling propellant. Okay, the plasma is being thrown through that, and the magnetic field lines are what's containing it. There is a coil that's helping to produce that field, and then down below you see that there's additional coils, and you see the B field there. That is, it doesn't show it, but that's actually rotating around. So very basic diagram. Okay, this is the part I'm actually most excited for. The experimental and speculative propulsion. There are other experimental propulsion methods, such as the use of black holes and the manipulation of space-time. Yes, highly speculative. I haven't been someplace where I've been able to see someone build it themselves, or demonstrate it to be possible, but it's part of ongoing research, and that's very exciting. So, given constant and consistent advancements in technology and AI material science, it could be possible that one or perhaps several of these propulsion methods will at last put the stars within our grasp. So, Alcubierre and Einstein-Rosen bridges. So, proposed by physicist Miguel Alcubierre, the Alcubierre drive is a theoretical propulsion mechanism manipulating space-time for faster-than-light travel. And through this theoretical drive, a space-time bubble is created around a spacecraft for propulsion. Now, there are some mathematics involved with this theory that I think is worth exploring here. The Alcubierre metric is a mathematical equation describing space-time expansion and contraction in the drive and around the spaceship. So that's expressed using the metric tensor, represented by the Greek letter alpha, in a 4x4 matrix encoding space-time geometry. What does that look like? So the Alcubierre metric here, I'm just gonna, this is actually from my blog, which you can explore later, but essentially this was influenced by solutions to Einstein's field equations, okay, and describes physics of uh, acceleration in a flat space-time. I'm sorry, that's the Rindler metric, that's here below. So the Rindler metric is related due to similar solutions to those field equations. So one of the ways that this is interesting, okay, is that it also applies to special relativity in the context of the twin paradox in the case of time dilation, which may occur in faster than light travel. So here, where it says ds squared, ds represents infinitesimal interval of space-time, you know, and what does that actually mean? Well, it's just saying that there's a specific amount of distance, and then this is how fast light is going to be traveling over time within this space. A is the function that actually describes the expansion and contraction of space-time, and then Lorentz transformations and differential geometry are used to extrapolate the further context of those expansion and contraction. Which brings me to wormholes. The Einstein-Rosen bridge equation. Very similarly, Einstein's theory of general relativity mathematically predicts the existence of wormholes and solutions to the field equations. So very similar to what the Alcubierre metric and Rindler had explores, except this equation describes the geometry of a static spherically symmetric wormhole. And one more here. I know some people are like, why all the math? Morris-Thorne equation. So here it describes the geometry of a dynamic traversable wormhole. Two ways a traversable wormhole would be ideal, as demonstrated in this example. We don't know if wormholes exist. We believe that we've created microscopic black holes and wormholes in the lab, but it's a matter of expanding those and making them actually usable. Let me see. Sorry, I'm kidding. There's one more. This one actually I find the most interesting of all the equations is the Guerra-Horowitz equation, because it's used to predict the behavior of gravitational waves produced by binary black hole systems, and it is utilized in quantum gravity modeling to explore space-time at the smallest scales, at Planck scale. So as far as Planck scale and what that has to do with binary black hole systems, it's predicting that um, the difference between 2 points in space, um, well, it's essentially that space can be contracted. Um, so there's the reference radius here, r, and then the radius at which something is being measured, and a potential difference. The exponential function is used to represent the dependence of those, and then the negative exponent suggests that those are inversely proportional. I think it's most promising to explore these equations because we have these new technologies and we have these concepts. It's just that everything is very spread out, and everything that is being worked on, people have their specialties or specializations. But as technology connects us more and more, there's more open interdisciplinary collaboration that's radically expanding our potential to have a rich civilian exploration of space. So, in conclusion, in practice, those theoretical frameworks, those are valuable tools for researching those scenarios. Um, as far as modeling, simulating, assessing the feasibility and limitations of those systems, and contributing to the understanding of the impact of travel on spacecraft directly from radiation, navigation issues, high gravity, power loss, etc. And if you would like to learn more about this topic, you can check out the source post on my Substack.
Wonderful. Tammy, thank you so much. So that was only a 20-minute presentation. So let me do this. First things first, I'm going to remove that. Everybody on YouTube, give Tammy an enormous applause. So normally, and actually Mark is in the studio too, he was applauding. Normally we have more people backstage today. It is not a large house, although I see all of them in chat, so they will get a swift reprimand next time I talk to them. But no, so we have all the usual suspects here, but they're actually watching on YouTube today. They're not backstage. So it's just you and me. So thank you. And as well to Mark, who presented earlier. You guys are just hitting it out of the park. So Tammy, we have extra time, and since it's just you and me, we can cause trouble. And actually, Mark is still backstage watching. Maybe we could bring him in a bit. But the first things first, I want to present. Let me see. Okay. So if it's okay, Tammy, can I present your interstellar space travel? I want to play this video. I'm going to leave the sound
Oh yeah,
off.
there's a video. That's why I couldn't
Yeah.
figure out how to play that.
Yeah, and hopefully this is streaming okay for us. And I'm going to show them your channel. And yeah, and that's okay. I try and keep the sound off. We get copyright strikes and weird stuff when we do that. So, but at least this way people can see that it's on your channel. I'm going to show them exactly where it is in a moment. I'm going to run them through all of your stuff as well. So this is a wonderful presentation that you put together.
Thank you.
You did.
Actually, speaking of AI tools, this video I used, Lumen 5 helped me put this together.
Oh, okay. Okay. Yeah, wonderful video. We're about halfway through it. It's nice to see all of the clips. Yeah. Well, you have a lot of thought and effort that went into this, and the presentation as well. Again, I can't thank you enough for doing this for us today.
Yeah, it's my pleasure. I love talking about this, and having this opportunity to share it with everyone is wonderful. So I appreciate the opportunity. Thank you.
Yeah, and I think it's also really great to do a run through on various methods of propulsion, right? Even if not all of those are anti-gravity warp drives or anything like that, it's good to be able to just, do a review of what's out there, just to remind folks that there are lots and lots of different ways to skin the proverbial cat.
Yeah, the way I see it is, we have we're already interstellar in a way, right? And so a lot of what I've proposed here are more a way of building the bridges that will get us into space, that will um, help us become interplanetary first and foremost, and then we can think about interstellar and warp drives. I think it depends really on the amount of resources that we're going to need, and the amount of energy we're going to need to harvest in order to make things like warp drives happen. And also, being in a space environment is perhaps safer than trying to attempt those kinds of experiments on Earth. So, some additional thought there.
Yeah. Well, so Tammy, this is your channel and it's youtube.com, the @ symbol hyperdrive anthropology. So if folks look, you can just look up Tammy Padina, look up your name on YouTube. That's how I found you. And so you have a small but growing YouTube channel. It is not all space, but that's awesome. And I see some playlists here as well, right? Like some machine learning and AI. If I understand correctly, these are probably not your videos, but this is a playlist that's curated. These are videos that you believe in. Same thing for math and science, right? These are
Uh,
videos that
yeah, honestly, I haven't watched everything, and I'm by no means an expert, but that's more like the University of YouTube section
yeah,
of my channel. So
yep.
yeah, but I really like much of the work I've done. All of these videos I've made for my Substack blog to be embedded in the
Okay.
different posts that they actually represent. And if you go to
Well,
the video, um, there's links to that. But yeah, like you can find me on Substack, hyperdriveanthropology.substack,
let
and
let's let's
I'm
go
trying to make an effort to write there.
let's go there next. So hyperdriveanthropology.substack.com. Okay, so this is the main page. We want folks to sign up there. But I'm already signed up, so I'm just gonna hit skip. So this is your Substack blog. These are your articles. This was actually where I found this was the presentation today. And so this started with a blog post. I want to show this to people quickly. And there are all the equations that are in your post. I know that you've extended things and added considerably more, but I wanted to walk people through this from the conference so that they could see, again, incredibly detailed work, Tammy. So it's wonderful, as well as wonderful references there. And my hope would be that the folks from this conference would help support what you're doing there by going to your blog. I'm messing myself up here. Okay, I'll just hit the back button. So the hyperdriveanthropology.substack.com. So my hope would be that they would visit that site and check out the various blog posts that you have. And you have several of those, many, many blog posts here. So we've got that. and then we also have meet and greet with Clubhouse. So this, you might have to help me with this. I'm going to put this in. This was one Clubhouse chat, right? It says this invite has expired, but you can still join the Hyperdrive Anthropology Clubhouse.
That's right. So if you go in there and you join it, then you'll get invitations. There it is.
Okay.
You'll get invitations to the next meet and greet, and that's about every 2 weeks. I'm not actually having one this week because the guests that I've invited, it's very important to me that they're able to make it. A lot of them are at Burning Man actually, and they're actually
That-
having their burn
That's why it's
today.
so quiet. Okay. Yes. Burning.
Yeah,
Yes.
yeah, perhaps there's that.
Yeah, well, I've had 2 physicists that I know actually email me from Burning Man, so you're absolutely right. I'd forgotten, but that's yeah. So when people scan this, and I'm not going to try and do that, online, but when they scan this, they can join Clubhouse, and just to, I guess, so that we're aware, Clubhouse is basically like an audio conference bridge. So it's similar to what we're doing here, but it's all audio based, right?
That's right. And what I like about it is um, I really like the interface on mobile. So I feel that I can participate pretty much anywhere. And so it's low bandwidth because of the audio, it's audio only. And there's just a lot of incredible spaces there. It's really quite fun. I'm actually considering creating another house that's based on rare diseases and genomics, because that's another passion of mine outside of futurism and space and physics. So, yeah.
Oops, and Tammy, you're fading out just a little bit. Sorry, I lost you for a sec. Oh, you're muted.
Can you hear me now?
There we go. Yeah. Okay. And what I'm gonna do,
All right.
because
So,
things are a little
yeah.
quiet, I'm gonna throw out. We'll do this a little early. I'm gonna throw out the StreamYard. This I'm putting this in there. This is the back end link. This is the studio link. So if anybody wants to join into the studio and chat with Tammy, we have some time before John Brandenburg arrives. And so I'm going to throw that link out. That's the studio link. I'll bring folks in. Let me see. Mark, do you think I could add you into the studio as well? Let me see. We still have Mark Calvo with us.
Hey, Mark.
Hi, Tammy.
Hi. Yeah, is it okay to bring you in? We could kind of do open discussion.
Okay, the Einstein-Rosen bridge equations that predicts wormholes. Do they have a specific size of wormholes that they're predicting? Bridge equations that predicts wormholes.
You'll have to forgive me because I'm no expert. I consider myself just a student of physics and space studies, but as far as I know, some interpretations of the Einstein field equations, according to those interpretations, wormholes are possible. But I think that those interpretations are sort of extrapolated from like an information theory sort of viewpoint. So what does that mean? I think we've been able to make these microscopic wormholes, supposedly, these observing these quantum mechanical effects. But as far as making something much larger, I'm uncertain because at certain energy levels, very large energy levels, we may not be able to, because we know that the mass energy equation kind of explodes after, faster than light. So to answer your question, I think that means that there must be something more, right, to that.
Yeah,
So
I'm in
in order
agreement with
for
that.
something to accelerate
It'll
beyond the
be,
speed of light.
if wormholes exist, it'll be microscopic, uh, micro wormhole tunnels.
Mhm.
Well, I just
But
read a paper that
as far as like effects of space time, yeah. Go ahead, Tim.
I just read a paper saying that that electrons might be able to keep nano wormholes open. Again, nanoscale, not large, but they were saying that the energy in
Mhm.
electrons might be able to keep them open instead of requiring negative energy, which would be awesome. So
One more comment though, like with Mark's work actually, which I found fascinating, with gravitons, is that looking at space time at the Planck scale, from what I understand, and I know so many people are going to hate on me for this, but with string theory, it might be possible that uh, Planck time may be malleable. So if that is at all possible, it could mean that we might have to reconsider how we look
Interesting.
at E equals mc squared. So
yeah. Well, so we have. Let me see. Mike Liloff popped in. Mike, you're on the holodeck today.
hey,
Did,
Yeah.
did,
that's cool.
did you have questions for Tammy? What do you have?
No, I'm still understanding most of this, watching carefully.
Oh, okay. Okay. Okay, well, let me mute you back out then. Um, well, so Tammy, what are you most excited about in terms of types of propulsion? I mean, because you've done basically a survey of what's out there. I mean, obviously rockets we're using today, but what are you most excited about?
Okay, this is going to sound extremely biased, but I am actually really excited for the microwave propulsion that I'm going to be working on Falcon Space with. So that sounds, but I am because uh, dynamic nuclear polarization, that might be a thing. We're going to find out.
Yeah, well, I think it is exciting. I think it is exciting, and I mean, what Mark was presenting about earlier, right, in terms of finding the right frequencies, seems like it dovetails in with what Mark is working on. It seems like there are so many things that are converging in on this idea, and there may be differences, right? I mean, like every model has differences, but the thing that I see is like a larger convergence of ideas, and for me, that's exciting. So,
Mhm.
well, what do you
Yeah,
think about
yeah.
fusion drives, though? I wanna ask about that. That is a now maybe I'll probably get beat up in this conference even talking about those, but I love fusion drives, because it's near term and it's practical, right? So, there's no magic required. We know that we can do it. It just takes, a lot of engineering.
That's a question for me. Um,
Well, I
okay, well, yeah, well, yeah, actually, I wanted to expand a little bit more on from what I've known from a survey of different fusion methods. As far as where the state of fusion as a viable way of harvesting energy, that really, whether or not it can be used in propulsion, is really dependent on that. And so currently, there are companies that are exploring ways of using AI in order to find ways of uh, containment in tokamak fusion reactors. And I think that's very promising towards the development of a actual working fusion model for propulsion. Um, but I think really like it may have to depend entirely on what materials we're going to be using because there's so much a there's a momentum transfer problem with fusion. We're dealing with the fusion is fusion of nuclei. And so being able to take that energy directly and transfer it into something that produces thrust is the primary problem. I think that there's a
Okay.
way to do that. It's just that as far as getting that to be like a propulsion device to like get us from Earth to space may not be as viable as something that gets us from like between planets, perhaps like as like an interstellar method. For instance, like what the Voyagers are doing. They're using a radioisotope, and I think they're using hydrazine thrusters. So there's as an energy source in order to move the spacecraft, yes, but perhaps not to get it, from the Earth to space, outside of Earth.
Okay. That makes sense. A fellow named Paul Sis did years ago. He had this idea for I'm forgetting the name of it, but he compared it to like an Earth to Mars railroad, right? Where you would basically have this fusion rocket that would go from Earth orbit to Mars and then back again in this big loop, right? And so that was his rail track idea. And like you're saying, it would never land on either planet. It would basically just go from one orbit to another, but then it would use these fusion drives and move really rapidly. So
Yeah, that's
interesting.
right.
Well, let me see. I should ask. So let me scroll through chat here. I don't want to leave out any questions. Um, and we have a healthy discussion going on in chat, although they seem to be getting distracted and going off on their own. Let me see. So Mark Fiorentino was saying faster than light travel can only be achieved by altering the space-time fabric, the aether, the properties of permittivity and permeability. Um, do you have any thoughts on that?
Well, that's sort of what I touched on with the Alcubierre metric and solutions to Einstein's field equations. I think the idea of being able to wrap a space-time bubble around a craft has to do with manipulation of certain qualities of space-time. With Mark's presentation here with gravitons, if we are able to find a way to pull that around a craft, that would actually preclude the actual manipulation of space-time. How that is achievable, very high quantities, vast quantities of energy. I don't have an exact figure, but I sort of agree with him that faster than light is something that could be, but that's theoretical as far as I know.
I want to show another one. Richard Muller said we need AI to navigate the universe, and actually, I think I think this is a brilliant insight because I think that's something that we haven't really considered yet, right? But AI is increasing so rapidly, and so when we get into advanced space propulsion, when we get into breakthroughs like this, um, this is something that we can utilize. I think he's completely correct. I think this could be an incredible leveraging technology. That wouldn't necessarily be propulsion, but in terms of like mapping stars and locations and things like that, that could be incredibly useful.
Actually, yes. And actually, Richard, I do agree that AI is one of the ways that we could build.
Oh, it looks like you're freezing a little bit again.
That was developed by the. Can you hear me now?
Yeah, you're back again.
It should be good now. Okay. Okay, good. So there is a quantum navigation system that was developed by the UK Navy very recently. And I think that such systems interfaced with artificial intelligence could be very helpful in order to map at certain speeds, because at that point, like, you're not able to use, human capabilities to figure out how to fly that thing, right? So you're just traveling so fast. So AI computationally would make sense.
Okay. Well, and let me see. I see Jeremiah pop here who doesn't want to come backstage. Why doesn't he want to come backstage? He's offering insightful comments, but he's doing it from the front of YouTube again. So, well, we have a few minutes. We have a few minutes left, but I think that we've run through all of our questions. So, why don't I do this, Tammy? If it's okay, unless you have anything else that you want to share, do you have anything you want to share or cover, or anything you want to promo during the conference?
Well, I think that pretty much does it for me. I actually, I don't really have any upcoming projects with my blog, but I really do appreciate if people would subscribe. I have a lot of free subscribers. I think I only have one paid subscriber. So if someone is able, oh, hey, look, there's Jeremiah.
There
Hi,
he is.
Yeah,
There
sorry,
he is.
I was, calmly hanging out in the YouTube chat, nice and
I know,
safe
and
in front of my computer, and I didn't have to put on a shirt. But as you see, I'm violating our main, prerogative of APEC norms by not showing up on camera. So I apologize for everybody. I don't feel like putting on a shirt because it's hot in here today. But today's presentations are fantastic. And I agree with the antimatter issue. There's a difficulty in actually getting out the positronium charge and separating our positron electron pairs in free space. And so many mechanisms have been proposed to try and do this more efficiently. And obviously, like what we do today, we're using certain selected radioactive elements that most of them are artificially made and producing small amounts of antimatter. But what we really need to do is find a way to do this with radio waves only without having to utilize special or custom-made isotopes that require particle accelerators to manufacture. And I think this is all possible because, quite frankly, like the 1.022 mega electron volt limit is not that high. I mean, it's quite achievable. So I know there's a better way to make the antimatter that we need on demand.
And what do you think that way might be?
Well, taking a look at some of the natural phenomena that we've observed, it seems like stimulation of certain crystalline structures that compress the electric and the magnetic fields in just the right way will create phase coherence and generate very, very tight packed light compression events, and they can reach these energy levels. So now we're getting to Jeremy Rys' special category of compressed or squeezed light, and I think that's the way we're going to find we can make this stuff on demand.
That would be amazing. That would be absolutely amazing.
I am working on a project with, thank you for actually mentioning that. I think that certain alloys, high entropy alloys in metamaterials might actually be able to achieve that. So there are effects at the nanophotonic junction that might be able to have those effects with stimulating certain crystals, certain materials. Yeah.
I would have to agree. And just think about what we've already discovered. There are plenty of patents where we have light-producing devices that can generate those missing terahertz wavelengths of almost any selection. Say, for example, sapphire being used as a maser generation source at a very tight threshold. So we know that already natural crystalline materials have the ability to amplify these effects. And we just need to find the right ones.
Well, thank you very much, Jeremiah, for jumping in and making that comment. That kind of made my day.
Thank you for your presentation and bringing all of this to our minds. We appreciate it far more. It's awesome.
Yeah, absolutely. Yeah,
thank
Tammy,
you guys.
thank you.
I really
yet
do
again.
appreciate
And
it.
I saw Terry Trevino as well, who's
worth looking at the things that have been done. Hi, Terry.
Yeah, I saw him. If he wants to pop in there, I just dropped the backstage link, and it's okay. He doesn't have to. He doesn't have to. We're kind of mellow today. We're mellow. I think we got nailed by Burning Man. Yeah. I think that's what's going on. So,
well, since we're simultaneously streaming on so many channels, let me poke the audience here. If anybody wants to, jump on here and let's talk metamaterials and possible solutions for how we reach these ultra high energy levels in compressed light states. If anybody wants to talk about that stuff, please let's start a discussion, because I'm no expert on it, but I would love to hear anybody's opinions, things that you've read, articles that you've seen, just about anything that might bring us one step closer to reaching those energy levels.
Yeah, well, and we could definitely do that. I mean, I'm totally open to it. And then the other thing was Phil Bouchard had asked to do kind of an updated presentation as well. And he's not scheduled. So normally we schedule for these webinars, we're trying to schedule things in advance now. But again, today's pretty mellow, so I would say, you know, let's do it.
I'd love to hear Phil's ideas about what he's working on with his gallium rotation system. He's already received what looks like some effects. I did want to ask him a couple of questions about his test setup, and one of the main ones is the thick, heavy wires with high current flowing. I mean, they literally jump. So I just wanted to verify that he's basically nulled out the potential contribution of that high current pushing down on the scale by those wires being attracted to each other and changing their shape.
Okay. Well, why don't we do that then? Why don't we do that? So you know what? Before anything else, so Phil is actually here. I'm going to add him into the stream. But again, guys, let's give Tammy an enormous applause. Tammy, you are wonderful and brilliant. Thank you so much. Thank you so much.
Thank you, guys. I really appreciate it.
Absolutely. Absolutely.
Yeah. Thanks, Tammy. I follow you on the other channel, the international organization for sustainable, space.
Oh, the UN thing, right?
Yeah,
the UN
yeah,
one?
yeah. So you're very popular already.
And prolific, and Tammy is everywhere all at once. So
yeah.
Everything everywhere.
Yeah. So yeah, it was for me. I wanted to hear about John first, but I can talk about my experiment first. Everything is ready already.
Yeah, if you guys want to jump into that, actually, I'm going to take myself off camera for just a moment. But yeah, if you guys want to just have an open discussion with Jeremiah, Tammy, do you want to stick around and discuss with them? You don't have to. There's no rule or requirement here.
I'm
I think
actually
we're kind of
take
open
a few minutes, but I'll be listening though.
Okay.
I really want to be here for this. I'll be right back.
Okay.
Fair enough. Yeah. So with your test setup, Phil, what's been going on? You made major progress. You finally got your gallium rotating at a decent velocity. I've seen your videos. I follow your channel and look at your work, and I'm pretty impressed that you're getting the good rotation. Unfortunately, you're fighting against gallium, and you'd have so much better luck with mercury if you wanted to, expose yourself potentially to the vapors, and you'll get a lot higher rotation. I was able to do it with about 10 times less energy than what you're having to pump into that gallium using mercury, because it's already going to be highly viscous or extremely low viscosity. It flows really easy at significantly less current. So you might want to play with that.
Interesting. Right now, I'm going to present my experiment first because a lot of people didn't see it yet. So just one sec. Okay, so partager l'écran. This window here, entire screen, there you go. All right, so here I am. So this is my experiment that Jeremiah is talking about. Sorry about the
ad. We don't have it on video yet. So Tim, as host, can you possibly get his video full screen here?
Can you see the video right now?
Not yet. We're just waiting for that changeover. He's got to select it and pop it up as full screen. I don't have the admin privileges here, so I can't do it.
Okay. So you see my face right now?
Yep. It's just you and me on the screen right now.
Okay. Yeah, let me send a WhatsApp message.
All right, he's got it.
Right. Okay. All right.
Yeah, sorry about that, guys.
So it works. Okay.
Yeah,
so,
you're full screen.
Okay, so here's the experiment. It's on pause right now because I want to explain what it is. What you see is a neodymium ring magnet. Underneath is gallium, liquid gallium, and underneath the liquid gallium there's another neodymium ring magnet. Each of one is 1.4 Tesla, so for a total of 3 Tesla. And the electric current flowing is 40 amps. So it's, you can see the gallium is spinning underneath. I'm there's a lamp, there's a reflection of the light of a lamp, and the wire, the gauge of the wire is too high, so it's kind of fuming right now because 40 amps is a lot of current. So yeah, that's the actual apparatus, and the result. What it does, it's on a balance. It's on a mechanical balance, and when I start the gallium, the gravitational weight actually shifts. So you can see it's a mechanical balance. So I mean, there's no electromagnetic interference or anything like that. I made sure it was on a mechanical balance just for that. So if you spin the gallium in one direction, it's actually going to increase the gravitational weight. If you spin it on the other direction, it's actually gonna decrease it. So that's exactly what I predicted in my calculation. But what I did not predict well is the actual current I needed to reach a certain speed.
Yeah,
So,
it's significantly high with gallium. It's just such a viscous material, and it really takes a lot to get it to flow. And by the way, if people watch that, if you're watching that video, you've seen his earlier demo where it looks like the gallium is moving, but you can't see it much. There's an oxide layer that really prevents us from seeing how fast it's moving, but it's a lot quicker underneath that oxide than it looks like, just so everyone knows.
Yeah. I wanted to integrate a flow meter, but I did try to. The best I could use is a thermal flow meter because it's a vertical stick. You just stick in, and you calculate the speed based on the. It's kind of a metal stick, that heated metal stick you stick in, and it cools down based on the velocity of the gallium. So it's very, very easy to integrate, but it's not that easy to find. I know it exists somewhere, but I'm going to try to find one at some point. There's the pitot tube also that it's possible, but it's a little bit big for the small opening that I have.
In measuring the velocity, I found that a fiberglass rod is actually very useful for this. It's been very helpful.
Fiberglass rod?
Yeah, I took these old fiberglass rods out of the inside of a Tektronix oscilloscope, old school version, the 400 series. And so those don't interact. They don't cool it down at all. They'll heat up to the same gallium temperature, and you'll be able to measure your velocity a lot better with something like that.
Oh, yeah, I'll check it out. Thanks. I'll note that down. Yeah, thanks, Jeremiah. And it doesn't look like it, but this experiment looks simple, but there's a lot of technicalities behind it. A friend of mine assisted me for it, and it's not that easy. So I respect every experimental physicist like you, Mark, and you, Jeremiah, for all your efforts on your experiments out there. So it's not that easy to get running.
It isn't easy at all. My big question for you is this, though, and this would be the obvious contributor to possible measures, errors in measurement, and that is the wires, of course. So you see that those wires jump, they're smoking, they're really moving around a lot. So how are you trying to nullify the contribution of the current flowing through those wires and the way that they might be pulling against each other and where they're attached to?
You mean nullify the magnetic field that it generates?
Not nullify the flux, but nullify the Lorentz force on those wires that may actually be pulling down or pulling up on that scale.
Not
on the scale itself, but just on the whole thing.
That's a great point. We also see with the scale results, it's not hanging in a weight loss situation, but it bounces between weight loss and weight gain, which is what you see when a object on a scale like that is perturbed. So.
Yeah, one possible solution to this would actually be one that Mark and I have played around with quite a bit, and that is having the battery system on board. So you don't need a lot of voltage. It's actually a very low voltage, but you do need a lot of current, and you'll have no problem cranking that current out with a nickel metal hydride cell that you could put directly on the device. that may be
Nickel-
the solution to solve this with a large, say, solenoid relay for automotive car starting. You can probably use something like that, and you'll totally fix all these possible error contributions and get a real measurement then.
Yeah.
Wonderful.
Yeah.
So
I just want to end that I'm gonna change the middle rings for zirconium rings because it won't interfere with the magnetic field, and I'm upgrading the power supply. But yeah, let's chat offline, Jeremiah.
Phil,
Yeah, well-
how much does the apparatus weigh? The
About 3.5 kilogram.
perfect. So you can get nickel metal hydride battery and put it on the other side as your counterweight, and that will remove any of these externalities.
That's a great
lead-
idea, Mark. That's a great idea.
Lead acid can work as well, but I would stay away from any lithium or anything like that because those have tendencies to blow up.
Yeah, thanks. I'll do that.
Yeah. So guys, I would love to come back. I'd like to bring all of you guys back on after John Brandenburg does his presentation. John is in the studio. Actually, I'm going to add him to the stream, but let me do this for right now. Let me remove you guys from the studio.
Let me turn off the light behind me.
And we'll come back. And again, thank you to Mark and Jeremiah and Phil for coming on. I would love to have you guys back to discuss the gallium stuff more in our lab section. I have John scheduled for 2, and he is right on schedule. So I will set this up really quick. I'll take him out of the studio. So physicist Dr. John Brandenburg is going to be discussing the gravity electromagnetism theory, which is a unified field theory that brings gravity, magnetism, electricity, and other forces into a single controllable force that can power all sorts of aircraft, spacecraft, and other vehicles, and could lead to a new form of electric spacecraft that will make rockets obsolete. GEM in its basic form gives a physical EM analog of gravity fields and evokes a Kaluza-Klein fifth dimension of a subatomic size, but much larger than the Planck length. So let me bring John in. So John, do you want to try and upload the PDF from your hard drive? That way you can flip through it.
Yes, if I could.
Okay, so click the present button.
Okay, present.
Yep. And then there should be slides. You see that little slide thing? And then when you click that, there's a little link down at the bottom that says from your computer.
Okay, it says your computer. Very good.
Yep, and it'll have you select the slide deck, and that way you can actually thumb through it left and right. Otherwise, I have to do it. It's a StreamYard.
Okay, yeah, that.
I know.
Very good.
Yeah,
okay, here, let me. Okay, let me upload the PDF.
Yeah, it'll be right there. Yeah, actually,
yeah.
Bernie
here,
Conkin got us into StreamYard, and I love it. I absolutely love it. Mark Sokol fell in love with it, and he got me into it, and I'm like, but it does
Mark is a really smart guy, so yeah.
Yeah, it's got a couple. It has its quirks, but I do love it. So
everything's got its quirks, including me.
Now you are not quirky at all.
Let me see if I can actually. I've got a video embedded in the.
So the
PowerPoint.
video won't
won't
play.
Yeah, here, hold on. Okay. You can upload 2 slide decks. Please log in or sign up to upload more. Okay. Anyway, so are we?
We can upload the video file separate.
Okay. Yeah,
is
it loading?
I'm not seeing it yet. It may take a second. We'll give it just a sec.
Yeah, it's a fairly big file. It may be too big. I may have to upload an PDF instead.
Yeah. Do you want to? Well, we'll give it a sec.
Yeah, I apologize for.
That's okay. I can upload your PDF if you want. Also.
Oh, okay.
Let me do that. I'm gonna have to thumb through it for you, but that's okay.
Okay, I'm sorry, Tim.
No, that's okay.
Okay, okay, very good, very good. Let me, let's see. Okay, present. I'm going to go slides to, okay, okay, wait a minute. There it is.
Yeah, that's the one I uploaded. So again, the video file that's embedded in this probably won't play. But what you can do is just I don't think that you
Let's
can
see.
go
Let
back.
me upload a slightly updated version.
Okay.
I've been very fortunate. I just got an article published in an Indian scientific journal called Fundamentals of Modern Physics. And anyway, okay, let's see. Okay, let me
Yeah, so again, it's that present button and then
present
slides
and then slides.
and from your
And
computer.
let's see if we can, okay, it says, okay, it says my computer.
Yep.
Add
And
slide,
then,
add file from my computer.
yeah, and that PDF
And
should go
okay,
right
it
up.
says upload file, and it should upload the PDF pretty quick. Pardon me. There's still problems with these systems, you know, that we're working with.
It's
Still problems.
You're doing great, John. You're doing great.
Okay, I hope to convince you all that we are on the verge of having electromagnetic control of space-time geometry, with all that implies. You might say that, okay, are you getting something?
I am not seeing it yet. Does it say that it's uploading?
It says having, okay, you're in the show. Everyone can see and hear you. Okay, let's just proceed with the presentation you have. It'll be fine.
Okay. Okay. So let me
I of course
put
wanted to add some, you know, little frosting flowers on the frosting on the cake, but no, we'll just skip that. We'll just have straight chocolate cake with vanilla frosting. There.
Everybody loves
And everyone will be
straight
happy.
chocolate cake. Everybody loves it. John,
Straight
let me do this.
chocolate cake with vanilla frosting.
I'm gonna mute myself.
Unfortunately.
I'm gonna mute myself out, but you can just say next. Just say next
Okay.
when you want me to go to the
Thank
next
you.
slide. Okay.
Thank you very much. Okay. Does everybody hear me? Anyway, yes, this is a modification of a presentation I gave to DARPA. They had given us a grant to study the theory of the GEM. Now, GEM theory stands for gravity electromagnetism, but its real meaning is in Latin. It's grandus et medianus, meaning the great, in this case, the Planck and the cosmic scales, unified with the mesoscale, which is the scale of atomics and classical particle sizes, which is basically the world we live in. So we're surrounded with this enormous universe. And then, of course, down below, at the very, very subscale of what I call the pixel size of the great reality program that we live in, is the Planck scale. And those are the great energy scales. And then we have the middle scale, which is where we live and where subatomic particles that we're familiar with, basically electrons, protons, neutrons, that they all exist. So the talk was about anticipating surprise. They gave me this grant from DARPA, and they said, don't do any experiments. So I said, yes, sir. Please sign my check. And I don't know why they didn't want me doing any experiments, but A voice inside me said, if you don't want a free bus ticket to Site 51 where they will never let you out, then do some experiments on this stuff, because this stuff works. Anyway, it's good physics. Okay, we're anticipating surprise. Next, with that introduction, next. Okay, I'm going to talk about, I'll introduce myself a little bit, then I'll talk about anticipating surprise, avoiding the Sputnik moment in the present day, or a Pearl Harbor, or another 9/11, let's put it that way. Okay, and then I'll talk about the requirement to search for a unified field theory of electromagnetism and gravity, the old Einstein quest, and the GEM, gravity, electromagnetism, or grandis et medianis unified field theory. And then I will talk about the propulsion technologies that this theory suggests we can develop. Then I will summarize. Yes, next. Okay, I am a theoretical plasma physicist specializing in controlled fusion energy and advanced space propulsion. I'm a plasma guy. Plasmas are, of course, lightning bolts, aurora borealis, the sun, the stars, and there are two big applications for plasma in present technology. One is controlled fusion, like the tokamak. We're making plasmas in there to kind of rival conditions in the sun and harness fusion. And we're going to succeed at that, by the way. We're going to succeed in that. We're going to stop global warming permanently. And then we're also using plasmas for space propulsion. So those are the two areas that I work in. I went to graduate school at Teller Tech. It was the extension campus of UC Davis at Lawrence Livermore National Lab in California. I went there in the 70s. I'm 70 years old. So I had, then I went from, after spending 6 years there, I went and spent 3 years at Sandia Labs in Albuquerque, working on controlled fusion and also directed energy weapons. So I spent 9.5 years at Nuclear Weapons Labs. I'll bring you up to date on some news items that draw on my experience there at Nuclear Weapons Labs. And I had a Q clearance. So anyway, I think that's kind of rather comical now because of this QAnon guy claims that he learned all this stuff with a Q clearance. I was told the world was flat and stay away from the edges when I basically was at Livermore as a graduate student. So anyway, having a Q clearance doesn't really mean that much in my experience. So I have had a career as a private defense contractor and at teaching in academia. And I was part of 2 space missions. One was called LACE, Low Amplitude Compensation Experiment. They were shining lasers from the ground and hoping to focus them using atmospheric compensation. And also then I was part of the Clementine lunar probe, where we discovered billions of tons, literally, of ice at the poles of the moon, buried under the dust. And of course, the Indian Space Agency has now landed a probe there and is looking for some of that ice. And I believe they will find it. I'm also the inventor of the microwave electrothermal thruster using water propellant that has now been successfully flown in space by Momentus. It's I have the original patent on it. It's expired, but the original patent is mine. So it creates a vortex stabilized microwave electrodeless discharge. And then we make plasma out of water vapor. It squirts out a nozzle and gives very high performance electric propulsion. And they've successfully flown into space on the Vigoride 5 spacecraft. So next. Anticipating surprise. I am part of the military-industrial complex. I say that without apology. We won the Cold War. We're dealing with other things now, other issues, let's say. Okay, now to avoid Sputnik moments or Pearl Harbors or 9/11s, you want to stay one step ahead of your adversaries. So you're looking for trends, you're looking for cumulative compiling analysis, and you have you try and stay very up to date, and you try and learn from whoever you can about things like energetic materials, matter, antimatter, fusion, fission, new propulsion concepts. That's what we were focused on. Novel approaches to energy storage and power generation. Next. Okay, we're dealing with a situation where we're encountering craft that appear to be able to fly around corners. They're flying what's called, you could call it inertialess drive. That is, they're apparently modifying space-time around themselves, so they behave as if they have no mass, and they're in free fall constantly. They can fly around corners very quickly as if they don't weigh anything. Because of the equivalence principle, if you can if you can change the space-time geometry around an object, then you can fool the universe into thinking it has no mass. And then you can also, and if it has no gravitational mass, it has no inertial mass either. You can have a 1,000-ton spaceship and make it theoretically to weigh less than a milligram. Next. Okay. Now we are looking for a theory that will enable us to do gravity modification. And there are four forces in nature. There's the strong force and the weak force, and they're short range. They hold, of course, the nucleus of atoms together. And the weak force mediates beta decay and basically the formation of the neutron, which is essential to having complicated nuclei. So, but we are interested in the long range forces of nature, and that's a pair of them. One is electromagnetism, one is gravity. Now, Einstein had figured out gravity with the general theory of relativity. He found the equations for the black hole, for gravity waves, for the perihelion advance of Mercury. His theory was very successful. And of course, with the verification of gravity waves in the last decade, his theory has been completely verified and shown to be very accurate. Now, he actually did that work in the 20s, and he then took up the task of trying to unify gravity and electromagnetism. So he figured out gravity. They had a good theory of electromagnetism, Maxwell's equations. And he wanted to see if he could unify those two forces. And since they both followed a 1 over r squared force law at low energies, he thought it was obvious they could be unified. And he also came up with an interesting idea. It's called the two-particle paradigm. Even back then, they understood because of his theory that there had been a Big Bang. They figured that out fairly quickly, and that the universe they could see was mostly hydrogen. So they speculated that the universe began with hydrogen and that the stars had then made more complicated nuclei, but everything started with hydrogen from the Big Bang. So you can imagine a situation where the universe is born with two long-range forces, E and M and gravity, and two particles, an electron and a proton. A heavy one that creates all the gravity, and a light one that creates all the electrodynamics. So Einstein attacked this problem. One of Einstein's problems, though, was he didn't like quantum mechanics. He said, God does not play dice with the universe, to which Niels Bohr, classic, replied in a big public debate, quit telling God what to do. And so he progressed on this to develop a theory that didn't involve quantum mechanics and tried to unify gravity and electromagnetism that way. Next. Now, I can report to you, I have found out that Einstein was basically right. You can develop a theory to unify gravity and electromagnetism. And one thing that gives you, that's very important to us, is it says that you can actually modify the geometry of space-time, that is gravity fields, with electromagnetic fields. So the theory that I have developed, and I'll be presenting in detail in a moment, is it unifies gravity and EM using a combination of other people's ideas besides Einstein's. Sakharov developed a zero-point fluctuation theory of gravity. Einstein was one of the first people to figure out that there was a zero-point fluctuation spectrum around us. And as I'll be showing you, Sakharov used that to develop a theory of gravity and linking gravity and electromagnetism. And then, of course, there was the Kaluza-Klein hidden dimension theories, which Einstein helped get published and basically embraced toward the end of his career. His last attempts to unify gravity and electromagnetism used Kaluza-Klein's hidden fifth dimension. Now, he didn't like the idea of a hidden fifth dimension. Einstein was kind of gee, if I can see it on the table, it's real. And even though he had actually explored, helped found quantum mechanics, he didn't like it. And so, but Kaluza-Klein, as I'll be showing you, got Einstein's interest, and he got it published. With his endorsement, it was published, even though a lot of people were deeply skeptical, that they thought it was just a mathematical trick. But the important thing for us now is that if you have a working gem theory, it says that gravity inertia modification technology is possible. And I will show you at the end through what's called a vacuum Bernoulli equation that unifies the effects of gravity and E&M in a way that can be used. Next. Okay. The problem that Einstein had was he was obsessed with the idea that quantum mechanics was some kind of, it was misleading, that the concepts of quantum mechanics were not physical, they were mathematical. And he kept saying, God doesn't play dice with the universe. And I've talked to Al about this, and I've said, Al, God may not play dice, but he does own a very fine casino, as it turns out. So the universe runs on quantum mechanics. It is reality. the reality we experience with our senses, which are optimized for this length scale, which I call the length and energy scale, which I call the mesoscale. We don't see quantum mechanics directly, except like in the black body spectrum, superconductivity, things like that. So what we see is only kind of the flowers. There's a whole bunch of everybody knows that roses have grow on thorn bushes, and so we look at the roses. We tend to neglect the stems, the stalks with the thorns on. Now the thorns are kind of quantum mechanics, and it's difficult to understand, but we can do it. We can do it. One of the key places where you can actually unify gravity with quantum mechanics is at the Planck scale, where you imagine quantum uncertainty allows you to form miniature subatomic black holes that appear and disappear due to quantum uncertainty. They appear to have a certain size, a Planck, what's called the Planck length, and they have a mass called the Planck mass, which is about sort of a milligram, even though the Planck length is like 10 to the minus 35th meters. And then they also have a Planck charge, which is not that far from the charges of the electron. It's the square root of the Planck's constant times c. So we have a Planck charge, a Planck mass, and a Planck length. And we then have, of course, the Hubble scale and the Planck scale, and that little place in between, marked life, that's where we live. Next. This is just a kind of brief write-up of our activities to do for DARPA. Next. Now, the basic gem theory relies on a discovery that I made as a plasma physicist, that there's a electromagnetic phenomenon in plasma physics called an E cross B drift, or you can call it a pointing drift. Pointing vector is the vector of momentum and energy flow in electromagnetic field. So it's E cross B. It's the same vector that carries radiation pressure. When you see the particles in space being pushed by the sun's light, they're being pushed by radiation pressure in the form of the pointing vector. So, but in quantum mechanics, not quantum mechanics, plasma physics, what's fascinating is that if you take an E cross B drift, it affects all charged particles the same. So next, we have I'm sorry, not quite yet. Go back to the same slide. I thought the next. So there's two postulates. One is that gravity fields are equivalent to an array of E cross B drifts. So you can make something that looks like a gravity field to charged particles, like protons and electrons. Now, the second postulate is that gravity and E&M exist as separate fields along with protons and electrons due to the existence and deployment of a hidden fifth dimension. Imagine your original space only had 4 space-time dimensions. There's nothing there. It's empty space. All that's there is quantum turbulence at the Planck scale. And then suddenly this fifth dimension appears and deploys. It gets much larger than the Planck scale. It explodes. It basically inflates, in fact. It's like the inflationary models of the whole universe. This dimension appears as a fifth dimension, and then it expands. It inflates. It sort of pops like popcorn. And suddenly, where you only had one field, let's say kind of some merger of gravity and E&M, and one type of particle, you had Planck masses and their antiparticles, and suddenly you have two forces, two long-range forces, E&M and gravity, where you only had one before that at the empty space of the Planck scale. So now you had started out with one force field, and now you have two long-range force fields, and you also started out with plus or minus versions of the Planck particle, antiparticle of the Planck mass, and they break apart and they form two separate particles, protons and electrons. So you suddenly, in the Big Bang moment, the thing that triggers the Big Bang is actually deployment and inflation, or popping out of this fifth dimension to some scale similar to the atomic scale or the particle scale, classical particle radius scale, which we call in the GEM theory the mesoscale. So fifth dimension appears, blows up from the Planck length and becomes the mesoscale, close to the classical radius of an electron or the nuclear radius of a proton. And at the same time, separate forces of gravity and E&M appear. So you have two separate, you started out with one particle, one force, and now you suddenly have two forces and two particles. So next. Okay, here is a diagram showing you the E cross B drift model of gravity. If you have two plates at different potentials, so you have an electric field between them and a magnetic field coming out of the screen, so the magnetic lines of force come out at right angles to the electric field, then if you put any particle in there, a charged uranium atom, an electron, a proton, a meson, they all end up drifting at the same velocity in the same direction. Now, if you take the two plates and tilt them well to each other so the electric field actually gets stronger down near the bottom, all the particles will accelerate at the same rate. You have an electromagnetic analog to gravity field that satisfies an equivalence principle. And you say, well, suppose the particles aren't charged. Well, in the beginning, and we're trying to keep this image of the universe simple, bingo, the universe is full of hydrogen. That's all charge. So the stable fundamental charges of, the stable particles of nature are all charged particles or composed of charged particles. You could say, well, what about the neutron? Isn't it stable? No, it isn't. It actually pops off like a firecracker after about 10 minutes. It lasts 10 minutes. There's a half-life of 10 minutes. But it will actually decay into hydrogen and a neutrino. So if you imagine that the fundamental makeup of nature, of matter, is charged particles, then they can all, in a strong enough a magnetic field and E cross B drift, they can all follow this electromagnetic analog to gravity. So let's just say that gravity itself is a creation of an array of E cross B drifts created by the 0-point fluctuation spectrum. And this approximation works really well if the electric fields are much weaker than the magnetic fields. So the fundamental nature of the 0-point fluctuation spectrum is magnetism. It's like there are a bunch of magnetic monopoles down there that we can't see, and that they're stable. But anyway, so we can make an electromagnetic analog to a gravity field, and you can do simulations. Here I show in the one side of the thing in gray. That's actually a result of a computer simulation, releasing an electron and then something about the mass of a meson that's positively charged, and having them both accelerate. The two lines are the two plates. So this thing works. You can simulate this. Another thing you can do is, instead of curving the plates, you can actually put a voltage ramp, like a sawtooth signal, on the two plates, so the electric field increases in time. And that will also accelerate the particles in time. So you can get an electromagnetic analog of gravity fields that satisfies the equivalence principle. Because in the frame of the moving charge, the velocity creates from the magnetic field, creates a opposing electric field. So the electric field actually vanishes in the frame of the particle, just like gravity fields vanish in the field in the inertial frame of a falling body. They become weightless. Next. Hello. Thank you. I'm sorry. It did change. Now, Sakharov came up with a very similar idea, only he imagined, rather than plates and electrodes filling space-time, he imagined just electromagnetic radiation from the 0-point fluctuation, which is predicted by quantum mechanics. We're surrounded with a sea of electromagnetism that we cannot perceive directly. We're like fish at the bottom of the Marianas Trench. We're surrounded by pressure, but we don't feel any pressure because the water inside our body is at the same pressure as the water outside our body, so we don't feel any pressure. So the 0-point fluctuation, which gives rise to Casimir forces, you can imagine two bright objects in a dark box. Let's say we're up at the space station and we're weightless. You put two white-hot spheres inside a dark box of metal. They will actually repel each other with mutual radiation pressure. Now, if you do the exact opposite experiment, you put two cold ball bearings inside or cold balls of like carbon that are black. You put them inside a box and heat the box electrically so it's white hot. They will actually attract one another with a 1/r² force. Now, Sakharov's original article showing this was very terse because he was trying to get it through Russian classification. Turns out the hydrogen bomb runs on radiation pressure. So he never mentions the term radiation pressure once, but he did derive a value for the value of G based on the Planck scale quantities, which unfortunately also include the value of big G, the Newton gravitation constant. So in one sense, you're hiding G on one side of the equation and having it pop out on the other. But anyway, so Sakharov did this, and then Hal Puthoff went and looked at Sakharov's model and really made it bright and shiny like the family silver, and showed that it was completely consistent with quantum mechanics of quantum electrodynamics. So that's so I call it the Sakharov-Puthoff theory, because one was just a very terse suggestion of Sakharov, and then Puthoff took the same Hal Puthoff involved in remote viewing, but he he made it a very precise mathematical derivation, whereas Sakharov's derivation is a little hand waving. So Puthoff published a very fancy version of Sakharov's idea, and it all works. So you can actually have an electromagnetic radiation pressure theory of gravity, where the radiation pressure arises from the vacuum 0-point energy. Next. So you have a pointing vector arising from the ZPF, and in an accelerated frame, you can show that there's also what's called the pointing Robertson effect, where if you're flying through a black body spectrum, it actually develops an opposing pointing vector. So what happens in the Puthoff, the Sakharov-Puthoff theory is in the frame of the moving charge particle, or particle receiving this radiation pressure, the radiation pressure actually vanishes as a net force. It becomes the same from the front as the back. So next. And it's easy to show that you can actually develop a 1/r² force from this radiation pressure model. In fact, this has been around for a long time. A fellow named Fascio developed it about the same time as Newton developed his mathematical theory of gravity. Next. Okay, now, if you develop this E cross B drift model of gravity, it gives you some nice math that you can then, you start out doing this math at the non-relativistic limit, which corresponds to E over B being much less than 1. And then you try and generalize that to be relativistically consistent. And as it turns out, what looks like the Newtonian potential turns into one element of the metric tensor of general relativity, Einstein's general relativity. And what's interesting is it forms a very compact form based on the E&M stress tensor of relativistic E&M. And so basically you have a fully general relativistic theory of gravity and E&M being related, where the metric tensor is due to a portion of the Maxwell stress tensor of electromagnetism. And one of the things that happens when you do this is that the 0-point fluctuation spectrum self-censors, it cancels. It's as if electromagnetism, due to the quantum 0-point fluctuation, which should give every piece of every cubic centimeter of vacuum the same weight as our galaxy, instead it creates anti-gravity as well as gravity, so the two effects cancel. So you can say that very, very early in this theory, you encounter the fact that electromagnetic fields can not only create gravity, they can cancel it. So that is what gives us hope that we'll be able to develop flight technology from some kind of unified field theory unifying E&M and gravity, where the metric tensor of gravity in general relativity is actually a form of the Maxwell stress tensor. Next. Okay, the second GEM postulate is that this appearance of this fifth dimension made protons and electrons appear separately out of the Planck scale as two separate particles, whereas before there had only been one particle with one mass. And not only that, but this then caused this fifth dimension to expand from the Planck scale and become what was called the mesoscale, R0. Now, what's interesting when it does that, it inflates. It actually expands at what would seem to be many times the speed of light. It basically pops out like popcorn to be, so it's not really a velocity. It's more, it's a popping up of, it's a popping of the dimension rather than a movement of anything. And so it ends up being like a frozen wavefront of electromagnetism, like an electromagnetic wave, where the points on the surface satisfy the equation of something like they're moving at the speed of light, and suddenly we're frozen. And what this means is that if you work out the details of this, the new hidden dimension physically is actually electric charge. It appears as a length because it's multiplied times a charge to mass ratio or charge to mass energy ratio. If you take a charge to mass energy ratio of like an electron and then multiply it times an electron charge, you get, as a result, in the CGS formula, you get the classical electron radius. You get a length. So it's actually physical. You actually, as long as you constantly use this conversion factor of a charge to mass energy ratio, then you get charge becomes lengths. And that's why you can call it a fifth dimension. So one other thing that happens, interestingly enough, is the charge, because it's expanding in a fourfold, it's expanding in a charge neutral way. Of course, the universe is charge balanced, but it's also expands at zero action, let's say minimum action, like in Lagrange principles. What happens is the charge actually the charge squared, or the charge, appears like a relativistic 4 vector. What that means is that not only does the sum of the charges equal 0, so it's got a 4 component in this charge space-time vector, and you have the charge of the electron, that's the spatial part of this space-time vector, but the charges of the quarks are the spatial part. So I'm sorry, the electron is the time-like part, and the quark charges are the space-time part. So this is why when you multiply, when you square the normalized charges of the quarks, 1/3 and 2/3, -1/3, 2/3, 2/3, for like making up a proton, then you have the charged electron. It gives you a length of a 4 vector that is 0. So not only does it have 0 displacement in this new fifth dimension, charge neutrality, but it gives you minimum action in the form of the charges squared all add up. It's 1 minus 4/9 and 1/9. So that's 4 minus 9/9, that's equals 0. So the quark charges are the spatial part of a 4 vector in this theory. And that's why we have what we have. Now, the second postulate basically says that the appearance of the fifth dimension and its inflation to subatomic size, the mesoscale from the Planck scale, is actually coupled to the appearance of the proton-electron mass ratio. So not only does the proton and electron get much lighter than the Planck length and Planck mass, but they actually develop a length, a mass ratio between themselves. And as it turns out in the theory, it's the square root of the mass ratio that is very important. The most important number in the universe. The answer to all the great questions. And it's the number 42, or actually closer to 43 if you round it, 42.85. And when I first developed this theory, and you'll see why I've stuck with it in just a moment, I had no idea about what the book Hitchhiker's Guide to the Galaxy was out there, and postulated the number 42 is the source of all truth in the universe. But as it turns out, it's the number 42. I'll show you where the number 42 comes from. It doesn't come from Alice in Wonderland, where the king tells Alice, who's in the courtroom at the end and is grown to large size, he says, Rule 42, all people more than a mile high must leave the courtroom. So that's the source of the number 42, apparently, for Hitchhiker's Guide. But the number 42 in the gem theory comes from the proton-electron mass ratio, which it turns out is deeply significant. I'll show you why. Next. Now, because of the basic part of the first part of the gem theory is that you can make gravity from electric and magnetic fields, an array of them. The second postulate basically says that the mass ratio of the electron to the proton, or at least its square root, is equal to the logarithm of the size of the mesoscale relative to the Planck scale, which it grew up from. And both sides of this equation are 42, as it turns out. Now, next thing. This is also coupled to a mass model where you have a basic mass called the mesoscale mass, m0. And if you multiply it times an exponential factor related to the charge, so that positive means it's 42 times larger than that, and a negative charge, a negative electron charge, means it's 42 times smaller than m0, then you get the proton and the electron masses from this. Now, the actual m0 can be derived from the Planck mass. And it has a correction term due to apparently quantum electrodynamics. If I had enough time, I'd explain the reason that must appear. But what happens is you can get the mesoscale mass from the effect of the Planck charge normalized to the electronic charge. So this gives you alpha, basically, or the square root of alpha. And so you get this mass formula for the proton. Now, we can then, or for the proton and electron system. Next. First of all, from the equation for relating the mass of the proton electron mass ratio, which is the square root of which is 42. If you relate that to the logarithm of the scale of the mesoscale mass over the Planck mass, and you must realize that it's a length scale, but it's also, since the mesoscale mass is determined as a classical particle radius, it's actually a ratio, the square root of a ratio of the strength of gravity between an electron and a proton and its electric forces. So you have two forces acting between an electron and a proton. One is electric, and the other one is gravitationally. And you can ratio those two forces. The ratio of the forces, take the logarithm of that, and that gives you actually. But you have to throw in the quantum mechanics of the electromagnetic field. So you end up multiplying this times, it's scaled by alpha. And what happens then is you can invert this formula, and you know what the logarithm of the ratio of these things is. So you can actually find a formula for the Newton gravitation constant from this theory. And you can see, unlike the Sakharov-Puthoff formula for big G, which showed, which basically hid the value of G in the Planck length and the Planck in the Planck length or Planck quantities, and then has it reappear as big G on one side of the equation. Here you have no Planck length. You have only the particle, the mass of the proton, mass of the electron, and alpha, and the electronic charge. And that's what gives you a formula for big G. And that formula for the Newton gravitation constant, which runs the universe, you get a value of about 6.668 from this formula. There's a small correction of the formula, which I've discovered, which gives you an even more accurate number. But for just today, it's just it comes in within a part per thousand just with this formula. As they say, close enough for government work. The actual value of big G is 6.6 times 7.4. That's the codata value. And we're getting about 6.668. Tongues will wag. It's got the 666 in it. That disappears, by the way, when you apply a correction term. So we can get big G from this theory, and we can get the mass of the proton from this theory. So, and they're both of those agree with reality to one, the mass of the proton is good to within 1/3%, and the mass of the value of the gravitation constant is good to within 0.1%, just even without any further corrections. So this is why I have stuck with this theory. It gives us not only a model for E&M gravity fields that can be modeled with electromagnetism, but it also gives us the value of big G and the mass of the proton to very high precision. And these are simple formulas. I presented this at an APS meeting, by the way, with a bunch of string theorists there. They paid me the ultimate compliments, you guys. They got mad at me. Real science is like professional basketball, you guys. It's not supposed to be a contact sport, but in the big leagues, in a close game at the end of a championship series, the knees and the elbows fly under the net. They do. So real big league physics involves people who are very passionate about their theories. I know I'm passionate about this. And particularly the string theory people are very frustrated right now because they can't, they haven't been able to show anything in the accelerator experiments or astrophysically that actually verifies their theories. So, but I got big G and the mass of the proton and displayed it at this conference in a poster session, and this attracted great hostility from people. One person accused me of mathematical sleight of hand. He said I'd hidden G on one side of this equation and made it pop out on the other. And I said, well, here's the formula. Show me where I've hidden it, where I've hidden G. And then his angry look slowly disappeared, and then he just walked away. So another fellow came up to my poster and started reading it. And I said, sir, can I help walk you through this theory? And he turned to me, he was a gray beard, and said, no, I can read it for myself. So guys, they paid me the ultimate compliment. Instead of rushing forward and shaking my hand, they got angry with me. Fortunately, I had a very attractive girlfriend with me, so everyone stayed very civil because for her sake. So anyway, next. Now, I've shown you that this theory, based on two postulates, which appear to be physically defensible and give good numbers. One shows how you can have a vacuum quantum mechanical turbulence around you, and then it can vanish and give no mass term. And so, why does the vacuum weigh nothing? Well, because of the gem theory. Then you also can say, the gem theory also says you can modify gravity with electromagnetism. But also it says that the universe began with one particle and one force, and because of the deployment of a fifth dimension, it ended up with two particles, basically hydrogen, electrons, and protons, and two forces, gravity and E and M. So now the theory seems to work pretty well, if I do say so myself. So now, what does it say about our ability as humanity to ultimately master space flight without propellant? That is, manipulating space-time itself rather than changing the momentum of our spacecraft by rocket propellant. How about if we change the momentum state of our spacecraft by changing space-time itself? So, as it turns out, we can develop what's called a vacuum Bernoulli equation. Now, to begin with, a very fundamental thing, if you do a Newtonian theory of light bending around the sun to move the stars, it actually gives you 1/2 of what is observed. Einstein's theory of general relativity gives you double the Newtonian result for the deflection of starlight, and that's because the actual full metric theory of gravity gives you an additional term of space-time change in addition to just what you would expect from Newtonian. So let's start by looking at how we know that gravity fields can change space-time, which is where electromagnetism lives. How about if we do the opposite? That electromagnetic radiation actually can change gravity in addition to gravity changing electromagnetism. Next. So what we do is we find out that we can take Maxwell's equations now the acceleration of gravity we can actually look at as due to the time rate of change of the E cross B vector, the pointing vector, and the divergence of the pointing vector we can look on as the change of mass within a volume. So next, after some mathematical manipulation, which is quite straightforward, by the way, it's nothing complicated. We combine the two expressions for the change in gravity in the gem theory and the change in gravity in Newtonian theory, and this is a Newtonian limit result. We integrate both sides. We end up with the fact that gravity fields are due to quantum E&M radiation fields, S vector, the pointing vector. So that squared divided by some energy density gives us the gravitational energy density. And this looks a lot like the Bernoulli equation, except where you have, let's say, static pressure is the gravity energy density, and rho v squared, the dynamic, the ram pressure, is the other part of the Bernoulli pressure, and the two can balance each other. This is why when air goes over a wing that's curved, the air flows more rapidly on the top of the wing than the bottom to get around the corner quicker, and you get lift. So in this equation, if you create a bunch of electromagnetic field, you can actually, what you do actually is you actually create increased local gravity. So you can look at all matter as where there's increased gravity fields as regions of intense electromagnetic turbulence. But as it turns out, the two things have an equivalence so that one has to equal the other. So they become a constant. When you add them together, they become a constant. Next. Now, how can we apply this? Well, let's say that the vacuum Bernoulli equation from the gem theory enables you to create what is effectively a layer of negative mass. Now, if you have positive masses in a gravity field, the gravity vector above the mass layer is actually less, or no, it's greater than it is below the mass layer. So when you move through the mass layer, gravity actually weakens. But in a negative mass layer, gravity actually gets stronger if you move through the layer down towards like the center of a planet. So if you create a region of stronger gravity fields using this electromagnetic effect from the gem theory, the vacuum Bernoulli effect, you can actually create effectively a surface of negative mass that is repelled by gravity. So you can actually create your own flying saucer by having an electromagnetic vortex underneath the saucer. Next. And the fields that you use to do this, the kind of a flying saucer type craft you would develop is actually a dome of like a conductor or even a superconductor. And it has basically three coils beneath it. And those three coils are energized with Tesla rotating three-phase power. And they create a pointing vortex And this actually creates stronger gravity underneath the saucer than above it. And so the saucer flies. It has a lifting force. Wouldn't old Nick Tesla be pleased by this? Yes, he probably guessed it already. Next. So we can actually do experiments. Unfortunately, this is a video, but we can put coils on very sensitive chemical scales. I mean, we have an effect apparently that makes gravity become less in the presence of these rotating electromagnetic three-phase fields of Tesla. So you take a three-phase Tesla power source, energize a coil with it. We did here with liquid metal contacts. We use Gallium instead of mercury, but we turned on the device, feeding the coil, and the coil lost several milligrams. And then we turned it off. This is a very sensitive chemical scale. We turned off the fields, and the coil regained the weight that it had lost. So we had proven in principle. Now, this experiment was done before I got the DARPA money. So I wasn't technically violating the contract of the DARPA in showing you this, because I did this experiment long before I got the DARPA money. Next. Now, I want you to know that if you go on the web to the Confluence Institute, there's a very smart fellow named Lance Williams who actually tested my formula for big G and found out, yes, it was quite accurate. And there's the link. If you go there, you'll discover that he has an essay where he compares a whole bunch of different formulas for big G, and mine is the closest. And so anyway, so that's good. Next. Okay, in summary, we're trying to avoid technological surprise. We don't want anybody showing up here with technologies that we can't understand and we can't emulate. And the human race, let's say hypothetically, we're not alone in the universe, hypothetically. And let's say hypothetically we get visitors. Then we try to duplicate their technology. We see them flying around, hypothetically, and we know then it can be done. So we do it ourselves, and we use a theory similar to the gem theory to do it. It appears that the gem theory can lead to technology that enables you to modify gravity and inertia in order to propel craft through space. The gem theory combines Sokov-Puthoff gravity model with Kaluza-Klein hidden dimension theory to unify gravity in M. It leads to models of gravity fields that show that the vacuum turbulence of quantum mechanics vanishes. And it also leads to accurate formulas for big G and the mass of the proton. So, and it predicts a vacuum Bernoulli equation, which, like the Bernoulli equation, allows you to develop airplanes and create flight. The vacuum Bernoulli equation here enables you to build spacecraft that look like saucers, as it turns out. So, with that, we have, I've gone a little bit over my time. I'm sorry. Anyway, do we have time, Tim, for a few questions?
Yeah, I would say let's do it. Let's do it. And we have the whole crew here. Should I bring people in?
Okay, and yeah, I'm sorry, is there any thing left in the
No, I think that's your final slide. So I'll tell you what.
Slide. Okay. Yeah,
What I want to do here is and we have the whole crew with us now. I'm going to ask everybody to turn
Oh,
their
great!
cameras on.
I'm deeply honored. That
So I'm going to bring the
this.
folks in here, and let me see. Okay, everybody, please put your hands together and give Dr. John
I'm deeply honored to be
an
presenting to you.
enormous applause.
Thank you for being interested.
Yeah, absolutely. John, thank you so much. Thank you so much. Well, in terms of Q&A, yeah, I would say, does anybody who's in the room, let me see. Yeah, Phil, go for it, sir.
Yes, Bill.
Yeah, well, what a great presentation. Thanks for
Thank you
that.
very much.
Yeah, great honor to have you aboard. I wrote also an entire theory based on gravito-electromagnetism that explains everything at the macro scale. The light bending basically is the gravity, Newtonian gravity plus the time dilation, which adds together. And I was wondering, do you have contact information to share, or can you share?
Oh yes, Tim should have my contact information. Please, and I just email me directly at Space Ranger 137. Space Ranger, the fine structure constant, or inverse of the fine, at yahoo.com. I'll be happy to answer any further questions.
Awesome, thanks, because I got tons of them. So
and certainly, if you want me to look at something, I'll certainly look at it. This is a large scale collaboration amongst all of humanity.
Yeah, it's very complementary to what I did because you explained the mass. I can't explain everything except the mass and why gravity adds together, whereas electrons are repelled, and gravity is attractive. So can you explain that part?
Oh well, the gravity is you could say the electromagnetic force is kind of the building block that gravity fields are built on. So gravity fields are a combination. They are a true electromagnetic effect. I have a demonstration I do. I show that magnets can pick up paper clips. Very good. And then I show that unfortunately magnets can't pick up paper, even though they can pick up paper clips. This shows you dramatically the difference between electric and magnetic forces. Then if you make some static electricity, you comb your hair, or if you have hair, you comb it. Then you wave the comb over the pieces of paper, and the pieces of paper are attracted to the comb. That's electric forces. Then you take a radiometer and you shine a flashlight at it. You show you can make it spin. This is not, of course, directly radiation pressure. It's actually more complicated than that, but not much more. It's basically you're showing that the stream of electromagnetic energy can create a force on an object in a near vacuum. So there's no magnets. There's no combing of hair to make static electricity. No, but you can still create a force at a distance.
Okay.
And that is the connection between gravity and electromagnetic forces. Okay. Electromagnetic forces can be viewed as due to radiation pressure of the 0-point fluctuation.
Okay, and the time is directly proportional to the gravity potential, I guess?
Yes.
Yeah.
I haven't worked on that part of the time dilation, basically because I've worked in the kind of non-relativistic limit. I'm interested in just flying to Mars right now. I don't need to go at the speed of light to do that. Now, let's say you can modify space-time with electromagnetism. You can bend space-time. Okay, that gives you anti-gravity. You can fly to Mars. If you want to fly to the stars, you've got to have full mastery of space-time geometry. So you can make your own wormholes. You can twist space-time into a pretzel, not just bend it. And that requires a lot more math, Phil. I haven't mastered that. I've brought some of my theory into agreement with general relativity, but I haven't been able to develop like how would you do time dilation with electromagnetic fields? I don't know how to do that yet.
Okay, interesting. Yeah, because for me, I see more gravity. Like, well, I'm not sure yet, but I see more gravity and time rate for like a virtual particle. But
oh yes, we're living. You know, for someone out in space, our clocks appear to be running slower because we're in this gravity, they're at the bottom of the gravity well. And I have not been able to, except in very abstract ways, show that. I don't understand the physical mechanism of that yet.
Okay, well, thanks. I'm in touch with important people, so maybe we can, resume at some point.
Well, I'd love to develop this theory more strongly. I say onward to Mars and then the stars.
Awesome. We're on the same page for that. All right. Thanks.
Well, yeah. So let's go down. Maybe let's go. Let me see. It's in Pacific time. It's 3:21. So why don't we go to the bottom of the hour if that's okay with questions, and then we can go back to lab updates and we can do open discussion. I mean, it's been again today is pretty mellow. Today this is casual Saturday for sure.
At the risk of spoiling the mellowness of today, I want to make an announcement.
Oh yeah.
Well,
let's hear it.
Yeah. Well, no. Come on. Okay. You know that I found evidence for a thermonuclear holocaust on Mars that changed Mars from being Earth-like to its present state. And this does not look like it was a natural event either. That's there. I'm just summarizing that very quickly. That happened about 500 million years ago. And I published a paper on that in International Journal of Astronomy and Astrophysics. I can give these things to Tim so he can post them on his website. Now, that happened 500 million years ago. Now, and I'll try to make this very quick. Avi Loeb has just published the analysis of his spheres that he recovered off of New Guinea, Papua New Guinea, and he recovered what looks like the molten remains of some objects that came from another star system, impacted the Earth's atmosphere at very high speed. And the ratio of iron, iron has many, because it's the most stable element, has many different stable isotopes. There's very characteristic fingerprint for anything from this solar system. These isotopes are completely different from anything in this solar system, meaning this is truly pieces of an interstellar object. Now, he did an analysis, they've done an analysis on the components of these spheres. There's a lot of iron, obviously, because that's how they pick them up with magnets from on the bottom of the ocean. But there's a lot of aluminum and titanium in them. It matches pretty much high strength alloys used in landing gear on jet airplanes. It's aluminum, steel with titanium and some vanadium and some other things, but it's mostly aluminum, steel. It's aluminum mixed with steel and with some titanium thrown in. That's what they use. Okay, now so that's those three things stick out in there that show this is not a meteorite. This looks like high tech alloy that got melted as it came into the atmosphere. This doesn't look like it was a meteor. It looks like it was a spaceship. There's 3 other things that are highly abundant, much greater than background. That is lithium, beryllium, and uranium. Now, I worked for 9.5 years at nuclear weapons labs. What do I know that's technological that uses a lot of uranium, lithium, and beryllium? And that's a hydrogen bomb. So this thing may have been carrying a nuclear weapon or weapons. I'm sorry, friends. When I give talks on this, I say, welcome to the cosmos, my friends. And I show them a clip from Star Wars of Luke Skywalker and Obi-Wan Kenobi, who kind of represents the God figure, walking into the bar at Mos Eisley Spaceport. And the band is playing, and it looks, Obi-Wan Kenobi says, we have to go in there to find a space pilot, but watch your step. This place can be a little bit rough. The message from Mars, the message perhaps from this spacecraft, is that we not only are not alone, but we live in a tough neighborhood. I'm sorry. The rest of the universe is just as fucked up as this place is, if that was possible. Because we're typical of intelligent life. You want to know what intelligent life acts like in the universe? Turn on the news. Okay, there, my speech is over. But check out the analysis of the spheres that Avi Loeb has now published. I'll actually put a link on to Tim. You can see lithium, beryllium, and uranium, in addition to titanium and steel and aluminum.
And remember, John, these are not the droids you're looking for.
That's
not
right.
The droids you're looking for. So,
if I may, I've got three things for you, John, and 4 things. After
I wanted to tell you all that, and I'm sorry, and I don't want to bum anybody out. I'm just saying what we're doing is serious work here, involving serious issues.
Bummed out or not, the facts are the facts. And if anybody in the audience is interested, in addition to the book that you released, John, about this, you've also done a very recent presentation. I think it was the last time you showed up at the APEC conference. You did a full presentation on these various elements, and a pretty darn good one at that. So if you guys are interested in more of it, check that out.
Yeah, I have a book called Death on Mars. You can imagine I've been looking at this problem for a long time, and also the impact on human society that this will have. And I wrote two books that everyone should look at. One is Death on Mars, find the discovery of a planetary nuclear massacre, apparently on Mars. The other is Cosmic Jesus.
If you wanted to, John, over there.
I was hoping. What's that?
If you wanted to, over there on the right-hand section of the private chat, if you wanted to post links to those 2 books on Amazon or wherever you haven't posted them, we can get those in on the main chat. They're
on Amazon. One is Cosmic Jesus, and the other one is Death on Mars. I present to you horror and hope. Okay, there, and I'll just leave it at that.
Yeah, and John, I'm going to bring this up really quick as well. I'm going to put this on the screen. Hopefully that looks okay. And so there is Death on Mars, the discovery of a planetary nuclear massacre by Dr. John E. Brandenburg. And then we scroll down, America at Armageddon. And actually, you have several others, and you've contributed to others as well. So,
hey, I like to write now. Ever since my second divorce, I spent a lot of time writing.
I wanted to really
keeps you out of trouble. Keeps you off the street.
It does keep me out of trouble. It does. I may be crazy, but at least I'm not lazy. But the other book is called Cosmic Jesus, because I wanted. I'll tell you. I spent my early 20s as a Pentecostal fundamentalist because my parents had joined a Pentecostal fundamentalist church. Hal Puthoff got involved in Scientology. I got involved in Pentecostal fundamentalism, And after a while, I left because I couldn't bear it anymore. And I heard 3 times from the pulpit, by the way, when I was a not an Islamic fundamentalist, a Pentecostal fundamentalist, that there was no extraterrestrial life, that all of it was here. And I thought, how does this guy know? You know, how does this guy who just went to Bible
Because
college
Cosmic
know?
Jesus told him.
So
Cosmic Jesus told him.
So I wrote the book Cosmic Jesus. It turns out the word for world that's translated into English, God did not speak in Shakespearean English, it turns out. He's the New Testament is written in Greek, and the word for world in all of these verses that are familiar to you, God so loved the world, and go out into all the world and preach the gospel to every creature. That word is the Greek word cosmos. That's what's translated as world. So Judeo-Christianity, which is the dominant religion in the West, is a cosmic religion, just like Hinduism and Buddhism. So the human race is actually well equipped psychologically to handle the fact that we're not alone. And unfortunately, the other shoe that drops is some of our neighbors may not be very nice. Okay, the Klingons are out there, the Romulans are out there. So are the Vulcans, and so are the Andorans, and they're nice. They make nice. So anyway, there.
Okay.
I believe the future of the human race will look like Star Trek, and I'm very hopeful. So let us proceed. Let us proceed.
If I may.
On that note, well, guys, why don't we do this? Why don't we give John one more hand, and then we will go to open discussion.
Thank you very much. You're very kind.
Let's do open discussion, and we can come back to lab updates later if anybody has anybody. We already did do some lab updates with Phil's work on gallium, but yeah. So open discussion, guys, go for it.
I have a number of questions for John, if that's all right.
Sure. Oh, Mike.
So,
yeah,
Mike, I'm developing the theory for you. I'm developing the theory.
Michael.
That's the best I can do. This computer's just not very good. Sorry.
Okay.
That's all right.
Yeah. I just got to get a new one soon, probably. The last 3 months. So like I was in Puerto Rico and there was some sort of cyber attack. It destroyed my old computer, and I got this little guy, which had some hardened like electronics and stuff, and it survived. But yeah, I mean it's not good. It's not great. Anyway, I'll probably upgrade because this thing is just so slow. It just slows down my whole workflow. But anyway, yeah, what was I saying?
I'm developing a theory for you, and I'm going to show it to you soon.
Yeah, for superconductors. Exciting.
Oh, that's right.
So, first off, thank you so much for your very thorough and detailed explanation of gem theory from a high level. And
thank you.
It gets the point across. That would explain the electrogravitics experiments. That would explain maybe the flux liner.
Yes.
Yeah.
I think it explains a lot.
Yeah. You'll be excited to know we have some tests in the works that should test this.
Oh, good.
Yeah.
Good.
So that's exciting.
Same on this end, like Michael's saying. Same on this end. We've been actually getting some pretty interesting results here, and we can get into those maybe a little bit later. I also
he may already have some for you. Yeah. Jeremiah's probably got some.
And John, I wanted to really compliment one thing that you pulled up in your presentation, and it was just fantastic. You show how these two carbon spheres were actually pushed together, almost in the same way that we see in a wave pool experiment when the box was heated through thermionic motion or Brownian motion. So that is an incredibly powerful real-life demonstration, a proof of this concept. And we don't really get to see these proofs a lot of times. We see generally theories in mathematics, but here was something that's incredibly important. And we've also seen these same effects. I want to point out Fail Forward Research, which is Wayne Ojna over there in Canada, who has been really pioneering this advancement in thermal effects and the transition states of liquid to gas or gas to plasma. And he's been noticing significant weight losses there that account for this missing energy. So there does seem to be a
Interesting.
significant amount of evidence building up on this. And I also wanted to point out, too, that Morgan Lynch has posted several questions here. He's got 5 questions for you. He says it's up to you if you want to answer them. These are in my
Okay,
time.
I'll do my best.
So I don't know, if Tim, if you wanted to pull that up. For my time, it's 4:57, and when he posted these, and it's now 5:35 for me.
Then Mark and Tammy look like they have questions too. I can just tell by their faces. So I'd like to hear their questions. But yes, go on.
Oh, Morgan Lynch had some questions.
Yeah.
Yeah, I can go to Morgan. Let me put Morgan's up there. So number 1 and 2. Aha. Okay. Does this give a correction to the Newtonian potential? Is this related to Dicks' formulation of GR based on vacuum polarization?
It is. I haven't studied Dicks' formulation carefully enough but I believe we're all converging on the same idea, that you can explain that this fabric of space-time is electromagnetic. Therefore, you can manipulate the geometry of space-time electromagnetically. And I believe that Dicks' formulation shows this also. You know, who cares if our predictions are different by 10%, as long as the thing flies.
Okay, so let me put that one down, and then let me see. Then number 3 was, if you had an expression over 1 over the r² force, what parameters go into the determination of Newton's constant? How do you define the E and B fields of the quantum vacuum?
I wrote a book actually on the gem theory, where I actually derived the components of the metric tensor from quantum Planck turbulence. And it does come out, I have to make some assumptions, but I do a detailed derivation of that. It's in the book, The Gem Theory, which is also on Amazon.com. It was published by a German publishing house. They like my name, Brandenburg. I'm actually about half Irish.
Don't tell anybody.
Yeah. Well, my family, my great-great-great-grandfather in Germany was named Solomon, which meant he was probably a Jewish convert to Catholicism. They were unhappy, and so they didn't. My great-grandfather and my great-great-uncle did not take off their hats for a Catholic procession, and therefore my family got kicked out of Germany because of that. That's all it took. Oh, we not only did not take off our hats for somebody, we shot our mouths off about it. Typical behavior of my family. And we got all our lands confiscated, and we're on a boat to what was then the 13 colonies very quickly to get out of Germany while the getting was good.
John, let me put up number 5 here also.
Yes.
Is this radiation pressure model the same or similar to quantized inertia? And then he's saying that Kaluza-Klein theories predict additional particles. Do you know the mass scale of these particles? And I can put the others up too. Do you want me to put them all up here? Let me.
Sure.
Oh, it only does one at a time.
Okay. I do believe it leads to quantized inertia, because it leads to quantized mass, and by equivalence, you then of course get quantized inertia. Okay. Kaluza-Klein theories predict additional particles. My theory does predict a particle that's 42 times the mass of the electron. They may have seen it, but then all discussion of it suddenly ceased. So that's a very easy thing to look for, and but I don't. So I do predict the mass of some subatomic particles, but they're the ones that already are known to exist. There's only one that doesn't exist, that has never been seen, that I do predict its mass, but it has not been reported. Well, actually, there was an initial report of something about the right size, and then suddenly I didn't hear anything more about it. And that can mean many things in this day and age. Many things.
Well,
Let me put it that
I
way.
just want to
It
point
could
out
mean
Gotta
that they
follow up.
just, it was a bad experiment, or it could mean that they took the program black, you know?
I got
I
a
just
follow-up
want to point
question to
out that
that.
when Jeremiah when he mentioned those, I put them right up, which is further evidence that I'm basically just a meat puppet. I keep telling people that. No one believes me, but
You're not a meat puppet. You're the best moderator that this community has ever seen, Tim. And I
just-
think that we can
he's like-
all agree.
he's
You are
like,
the
put those
best mod.
questions up, they're up, right? I'm like, like Keanu Reeves, kind of. Oh, I mean, not. I didn't say that out loud.
Dude, you're excellent. We would never have found a better host. There is nobody I can
There you
think
go,
that would do
Jim.
this job better.
You're doing a great
Well,
job, Jim.
thank you. That's very thoughtful, but yeah, it's day to day, right? It's day to day, but we're getting there. Our community is growing. I mean, on that note, we're having several hundred people sign up a month. Now, they don't all like attend all at once, especially now that we're doing YouTube. A lot of them are watching on YouTube, and they don't all do it live. They do it over a period of like a week. I've noticed that with their stats, but so
John, regarding
Yes, Mike.
your derivation using quantum vacuum fluctuations, can you pull out the ratio of the strength of the electromagnetic force to the gravitational force by
Yes, I can. And,
okay, cool, awesome.
And it actually is an exponential factor related to, as it turns out, the ratio of the proton mass to the electron mass that has such a central part of my theory. And, you know, it was, I approached it phenomenologically. I said, well, it is what it is. And it's the square root of it just happens to be 42, like in Alice in Wonderland, but, or Hitchhiker's Guide. But as it turns out, I have found out where that comes from. It is the square root of the mass ratio of the proton and electron is 42.85. But the actual mass ratio of the proton and the electron is given to 13 parts per million. One of the great peculiarities of physics by what's called the Lenz formula, which was discovered in 1951 by a German physicist named Friedrich Lenz. He'd probably just gotten back from the Eastern Front and went back to trying to make life normal again in Germany. And it is the ratio of the proton and electron mass is given to 13 parts per million, or rather like 18 parts per million, by the number 6 times pi to the 5th power.
That reminds me
very, very close to what is observed.
Thank you so much for clarifying the uncertainty in the measurement. We seldom get to hear that either. That's so important.
As it turns out, you can actually derive, and where you think 6 times pi to the 5th, what kind of number is that? It's pi to the 5th power. That means some kind of 5-dimensional rotation, something like that. As it turns out, I found where that comes from. That comes from, brace yourselves, Planck's theory of quantum electromagnetic fields, the Stefan Boltzmann constant.
Oh, wow.
Look into that, written without h bar, but with just h. It has 6 times pi to the 5th power in it. If you take a proton as a ball of gluons that are like photons, they obey the same quantum mechanical statistics as photon fields. You have a Planckian distribution of 3 distributions inside a thing the size of a classical electron radius. As it turns out, you can derive the mass ratio as 6 times pi to the 5th. And it comes from Planck's derivation of the black body spectrum.
Interesting.
that underlies almost all the physics of the universe we see.
So you're sort of
everything
treating
from starlights to everything.
So at a high level, you're sort of treating these particles like droplets of plasma with
yes,
lots of
with black body spectrums inside.
Okay, so and that makes sense because then with the E cross B drift, they'll all drift in that same
yes.
direction. So then, what was my other question? So it does the. Do we get like 1/137, the Planck's constant? Do we get that from an effective plasma refractive index at that size scale?
You know.
Actually, yeah, that was my question. That was my question.
I can't really derive the 137 number from my theory, so that I can derive the mass ratio of the proton and electron, but I can't.
Maybe we can help you with that. But let me restate my question differently. Adding this extra dimension associated with charge.
Yes.
How does that differ from non-Euclidean geometry of space-time or variable refractive index model? So you have like with Einstein's experiments, like when you spin an object, then the radius, the circumference changes with associated with relativity and stuff, for example. But also when you have these particles, you get a non-Euclidean geometry to it. How does adding an extra dimension compare to just having a non-Euclidean geometry?
Mike, I'm not really sure. What I have focused on, I'm a plasma physicist, which are, we have to be. We're constantly trying to solve practical problems. So I like kind of physical examples of things. The nearest physical analog I can come up to, like the hidden dimension. And the thing is, the hidden dimension manifests itself in space-time, four-dimensional space-time, but it's kind of limited, so it actually looks like an object in space-time, not as
it's quantized.
Yeah,
charge
another
is
dimension.
Quantized.
Yeah, it's quantized. So it's actually much more like a hydrogen atom or a molecule, which we still can't perceive with human senses, but is part of reality. So we have this hidden dimension. Even though it's hidden, it's still part of reality. And it manifests itself in space-time as a complex object, because it's like when it pops out of this Planck length and becomes a finite sized, what we would call a finite sized object, it does so in a way that's completely uncorrelated with space-time geometry. Here's in fact the best example I can come up with, and I know this is going to sound very abstract, but if you have objects that have locations in space and time, and then you give them names, in the dimension of names, they don't move in X, Y, or Z or time, but they do have an identity. And that gives an X, you can think of that as another dimension. So you understand that? I mean, if you have red, green, and blue spheres. You can say, well, in the dimension of color, let's like quark theory, they're expressing a new degree of freedom, even though their space-time location does not change. Their color changed. And that meant that's what a hidden dimension looks like when you see it. It takes on a different identity, but it doesn't move in our dimensions. You see what I mean?
But I mean, are we talking about
like if you can't?
I mean, we're not. But there must be some, like, when you're adding a dimension to a space, I would assume that there's some continuously differentiable manifold that describes, and then so like it's the second quantization in quantum mechanics. There's some smoothing associated with these quanta, right?
I think that they're, Mike, you've invoked quantum mechanics, and that's a good way to answer any question that's baffling. Well, it's obviously due to quantum mechanics. There's my answer.
I always wonder if we get measurement errors due to the divergence and the way that we set up our measurement tools when it comes down to trying to take these very, very small pieces of data. Yeah. We do have another question, too, from the audience. I'm not sure if this is directed towards me or you, but yeah, I'm going to say his name wrong, so I apologize already. Yakute001. He says, I have a question. Is it possible that the general theories of relativity and quantum mechanics could be considered in this frame to be combined as the same theory?
I think that the best place to see that quantum mechanics and general relativity can come together is at the Planck scale. I mean, you have the Planck length, the Planck mass, and the Planck charge, and these are quantized quantities. They rely on Planck's constant for their existence. So we can actually quantize gravity at the Planck scale. It's just trying to quantize it any place else. Well, here's what gives me hope, by the way. We know we could quantize the electromagnetic field. That's what Planck did. And that's where, of course, the 6 pi to the 5th mass ratio of the proton electron actually hides, is in the Stefan Boltzmann constant that is derived precisely by Max Planck. Before it was just a laboratory observation. It was a constant derived from laboratory experiments, but Planck showed how you actually derived it using his constant from precise mathematics. So it's 6 pi to the 5th is part of that formula. So you can quantize electromagnetic fields. In fact, you can even construct a physical model of gravity fields based on like dark objects in a bright box or dark objects in a bright universe shadowing each other and being pushed together by radiation pressure from the surrounding universe.
Oh, that does lead to a really interesting question too, John, especially with the carbon experiment. So I'm assuming that these were buckyball formations that were utilized in that carbon experiment.
No, we didn't actually do that experiment. It's more of a Gedanken, a thought experiment.
Oh, I thought that this was
so it remains for someone to do this experiment. But,
I'll take that on.
Here's the thing. We can quantize E&M and finally develop quantum electrodynamics, which adds electrons zipping around inside the electromagnetic fields. Okay, the quantum theory of that is the most precise theory in physics. Beautifully put together by Feynman and some other guys, but we remember Feynman because he had the most electric personality. So we can quantize E&M. Now, if we can unify E&M with gravity, then we can quantize gravity because we can quantize E&M. That's my strategy.
So gem theory is not yet fully integrated with quantum mechanics then?
It is to an extent, yes, it is integrated, but you know what I refer to this theory as? It's a Bohr model of unification. Like Bohr came up with the model for the hydrogen atom. It predicted the spectrum. It did all of this stuff, but physically, as a model, it began to show its drawbacks. You know, they imagined the electrons moving in orbits like planets. That's when you do second quantization, then you get the balls of fuzz, the quantum fuzz, the wave function from Schrodinger. So this model of mine for quantizing or unifying gravity and electromagnetism, I refer to as a Bohr model. It's basically, gosh, it gives you some nice numbers. It gives you basic physical understanding, but it needs much more development, much more.
Gotcha.
And unfortunately, I am not a quantum field theorist. I am a plasma physicist. So
we've got to talk too, John. By the way, John, at some point, maybe by email, because I've done quite a few plasma experiments, and I've already seen warp field dynamic effects from those experiments, just using cold plasma and high velocity accelerated electrons within a small test apparatus on my modified or upgraded White Juday warp field interferometer. And I've gotten as much as 25
Jeremiah speaking exotic propulsion. Okay, thank you. Yes, let us communicate.
So guys, if I could jump in real quick, I'm just trying to get where is it? I wanted to show you. There it is. Okay. So I have a couple. Let me post this. Just a couple of quick news items here for everybody, because you guys know I love cheesy news. But I'll start with this. So if anybody missed it, the DoD launched the Arrow website. Just so you guys know, for all the UFO stuff, it is at www.arrow.mil.
How hilarious!
Yes, so that has and this is that okay? It's sure.
They've decided to change the name from UFOs to UAPs. Now they're going to change it to something else.
They're still saying
so
UAP
it presents
here.
a moving target. You know.
Oh, sorry.
It's,
and
Anomaly Resolution Office, ARO. There.
They also have, let me spread this out a little bit so you guys can see it. They also have a PowerPoint. I dropped a link in there that outlines their mission with lots of cool looking graphs.
The mission is to obfuscate and confiscate.
Yes, that's right. So they've got that. And actually what I wanted to, I'll just put this up really quick. I just saw this in the news headlines. This is my humor for the day. You guys know that I try and inject a little humor here.
He's absolutely.
Russia says it's actually good that its lander crashed into the moon and blew up. So there you go.
Vladimir Putin himself signed this press release.
We know that the way to the stars is through the thorns. So.
Wow, that's so well said.
That's a very Russian thing to say.
Yeah. So there you go. Here, I'll stop sharing now. I just thought I saw the bite one. I saw that bite article in Russia, and I was like, that one needs some attention. That needs some airtime.
It does.
I did, John. Actually, this isn't old news. This isn't news. It's from 2021, but this might interest you. I did an interview with a fellow this week. He's a science fiction writer. I forgot his name, but he did an article on physicists predict that you could send an electron through a wormhole and that the charge to mass ratio would allow it to transit without negative energy. A nano wormhole.
Interesting. That's a very interesting. Yes, I'm convinced that in fact, I've actually presented papers where if you develop a spinning electromagnetic field, so it creates an electromagnetic vortex, you can then create a wormhole, and what you're doing basically is you're creating a centrifugal force in the wormhole that keeps it from collapsing.
That's what Eric Davis wrote. Eric Davis wrote that years ago also.
Oh, well, Eric Davis and I actually agree on something. That's
yes,
good.
Yes. Eric Davis
this is a
believed
good
the
sign.
same thing.
Yeah, Tim, I agree with that.
He's a really smart guy.
Tim, I agree with that as well.
There you go. There you go. So
All right, Mark.
The chart I showed you about the micro wormhole tunnel has a shield of electrons around it, enabling it to sustain itself. And then when it gets out of a gravitational field or anti-gravitational field, collapses. And then the burst of microwave is emitted from that. Those electrons. Yes.
You know,
so when you come out of you get in your spaceship and you fly down this wormhole, and then you come out on the other side, it makes a kind of a burst of radiation.
Unfortunately, John, these are micro wormholes.
Oh,
very small spaceship.
You know, they're very tiny black holes emitted out of anti-gravity galaxies, or white holes emitted out of our own black hole galaxy. You know, it's just very tiny micro wormhole tunnels with electrons.
Well, we got to work on the scaling this thing up here, Mark.
The thing that excites me though about all of this is back when I was doing American Anti-Gravity, right, in the early 2000s, I was trying to do stories and research on this, and I couldn't find anything. And I asked a lot of physicists about it, and I may have asked you back then, but I asked many physicists about it, and they were just like, we don't know. Science isn't there. It's not there yet. And so what's exciting now is science is starting to make predictions, right? And that, for me, I'm like, this was just like it was going off the edge of a cliff 20 years ago, and now there are at least ideas on how it can work. That's really exciting.
Mark, I want to encourage you to keep pursuing that model, because we know that, you know, like superconductivity is quantum mechanics expanded to be macroscopic. So we can expand the micro into the macro.
And with that same thought, we can also start to finally tackle this major issue with like the Paklanov experiments, as an example, where he's received macro scale effects from nanoscale phenomena.
Well,
I believe so.
Yeah, and that takes us back to spin, and
I got a question.
Spin is fundamentally different than angular momentum, right? It's not constrained linear momentum. That's something that
no, it is not.
Yeah.
I see Mike raising his hand too, so go ahead.
Mike, what do you got?
Hey guys, can I ask, it's about the electron, specifically about the electron and its size.
Right.
From the macro to the micro, from the quantum to the macro. I mean, does the size of the electron change?
Well, let's say the size of the electron starts out.
The size, its dimensions in any way.
I think no. The reason I would say that, and John, you may disagree with me. Hopefully, I'm not wrong, but there's an idea out there called every electron is the same electron,
right?
And the reason was because they all measure identically. So I would say no, the size doesn't change.
So that's still the standard theory?
I think so.
Well, yeah, there's a theory that there's like electrons moving backwards and forwards in time, and that's positrons and electrons, and occasionally they run into each other and we get a bunch of gamma rays, you know.
I got one more.
Electrons going forward and backwards in time. So it's I think in my model, the electron starts out as the size of the Planck scale, and then basically blossoms or pops like popcorn to be the size of the mesoscale. What's interesting is if you take the classical radius of an electron, determined by its electrostatic energy, it turns out to be there's a factor of 1/2 that appears, so it's about 1.4 Fermis, 1.4 femtometers, and that's almost exactly the radius of the neutron and the proton in these nuclear drop models.
Hey, why are they the same size almost?
I thought that
in the gem theory, they're the same size because the quarks, you know, you've got a proton made of 3 quarks, or even a proton made of 3 quarks. They are actually the spatial part of a 4 vector that is actually shared with the electrons. So the electron's manifestation in space-time is as a 3-dimensional object, like a little sphere, like the Thomson cross-section. I mean, you know, you shine a laser into, you can actually bounce a laser light off a single electron in a chamber, and the cross-section of the electron turns out to be this classical electron radius, and it turns out that's almost exactly the radius of a proton, even though they have supposedly completely different physics.
I thought that the proton radius was smaller.
No.
The heavier mass. No? Huh.
Nope.
Is that what led?
No, it's
incredible.
in terms of quantum mechanics, in terms of light scattering, yes, it would have a smaller Thomson cross section, but according to nuclear drop models, the way the radius of a nucleus is determined by how many protons and neutrons it has in it, each occupying like a sphere, and then they take that to the 1/3 power, and that gives you the let's see, yeah, it gives you. Let's see if I'm trying to remember exactly. But anyway, look up electron radius models. I mean, not nuclear radius models or nuclear drop models. It turns out the radius of a nucleon, a proton or a neutron in a stable nucleus, is almost exactly 1.4 femtometers. And that's almost exactly the same radius as you get from an electrostatic model of an electron as a shell of charge.
Well, this changes everything then, because now what we're talking about is that it's the Coulomb scalar charge of these particles that might actually be defining their radii. And so now we have a totally different way to look at this. This is remarkable.
Oh, it is.
Tim, is Brian Kelly in the back room? I would love to have him in here because he's got a really brilliant theory. And if we can get him sort of in an impromptu presentation, that would be fantastic.
Sorry,
who's this guy?
Brian Kelly.
Do you suppose that by determining that all the electrons are the same shape?
Well, if Brian is here
to determine,
maybe post that link again.
That the electrons are really just the same electron because they're all the same shape. That's what led them to believe.
Well, you know, you can go down to hardware. You can go down to hardware store.
I mean, the same size and dimension. If they're not, if they're different, if they're two separate electrons, you would find something different, but you're not. So that leads you to believe or theorize that it has to be the same electron, right? Is that what led them down that path when they made those observations of the size and dimensions of the electron at the?
Well, Mike, but Mike, nature at macroscopic scale presents a whole bunch of stuff that comes in standard sizes, like an orange.
Does that dimension stay the same for the electron in the quantum area?
It's quantized because
okay, and I'm going to have to remove. Let me see. I have to kick somebody there. Okay. About, so Brian, give it a try now if you want to enter. And Andrew Arigma
is spacing time relative to each other.
Does anybody want to bail out? Because I got to free up a couple of seats here.
There was this idea that if I forget the scientist who came up with it, but there's this idea that if you have a magnetic monopole anywhere in the universe, then all charge must be quantized. Who was that?
Yeah.
Who did that again? But
Dirac. I think it was Dirac. Dirac.
Yeah, Dirac. Yeah.
Who is a really smart guy.
Yeah. So Dirac came up with that, and I mean, it turns out that we do have magnetic monopoles, at least as charge images in topological insulators. So.
Oh, interesting.
Yeah. So they do show up in that context because in this topological insulator surface, you necessarily, I mean, so it's just how the electric charge interacts with the the spins have to be oriented along the surface in a special way. So you get this charge distribution that shows up like that. But anyway, yeah. that's the idea.
And let me see. I'm going to see if I can get Andrew in here as well.
Pardon me for
Okay.
just a minute, gentlemen, while I step down the hall.
Okay.
I'll be right
I
back.
still have one
while
more question
sort
for
out
you,
everything.
but I can't remember right off the top of my head at the moment. So
Good. Remember while I am stepping down the hall.
all right.
I do have a comment.
If
Oh,
it's the
Tammy,
same
well,
electron everywhere,
while we're waiting,
Sorry,
Tammy,
I'm trying to
be
free up.
moving
I'm trying to
faster
free up
than light.
space here a little bit. So does anybody want to peel out? I think Andrew is going to come on. Is anybody done? You guys want to peel out for now? Probably want to free up one more seat if I can.
Yeah, I do have a few lab updates as well. If anybody was curious about.
Yeah, go for it. Go for it, Jeremiah.
Tim,
And I'm waiting for.
fill out.
Okay, Jared.
Thanks,
Thank you,
Jared.
sir.
I'm not sure what's going on.
Excellent.
And when John comes back, I think we need to give. Oh, I guess we did give him a hand. We did give him a hand for his presentation.
Oh
That's
yeah, excellent work there. And the other guy who was Mark, I took a quick look at his stuff at double speed before I jumped into John Brandenburg's presentation. I'm gonna have to look at that more thoroughly to formulate any questions for him. But Tammy, regarding the breakthrough starshot concept. There was something a couple years ago from the Estes Park conference where they were able to show that a what do you call it? The if you use a large magnetic field over, oh, you're getting an echo, Tammy. Do you mind muting yourself for a moment? Okay, thank you. So if you get a large magnetic field distributed over a large area of space, then just like a solar sail, it'll reflect or it'll accelerate some of the solar wind. And in fact, that solar wind effect is about 10x the photon pressure. So if you want to use a solar sail to slingshot around the sun, you might as well use a magnetic sail instead. And on top of that, they were just using the normal solar wind in their calculations, so they get 10x better than they get 10x better than a light sail that way. But on top of that, if you then if you can predict or alter solar weather, then you can make sure that your probe is flying off when coronal mass ejection is going on. So then you can multiply your solar wind pressure by a factor of another factor of 10 to 100, depending on the coronal mass ejection and where you place the thing in the solar wind. So now you're talking about breakthrough starshot with 10 to 100x the acceleration, actually 100 to 1000x. The acceleration of the normal breakthrough starshot. And then on top of that, you could place a hydrogen beam instead of a laser. So you have something accelerating using basically its own, what do you call those things? You could have some array of ion propulsion systems shooting a beam of ions at your magnetic solar sail, and that too will have a lot more propulsive efficiency, or I mean, you'll have a lot more propulsion force than if you just had a gigawatt ground-based laser.
Yes.
So basically, you can take that breakthrough starshot thing, multiply the acceleration factor by like 1,000 maybe, and probably have a lower power output on the front side. You could put your ion propulsion on a big asteroid so that it doesn't drift much, and then now you've got breakthrough starshot in like 1/10 the time or better. So like a few years to Alpha Centauri instead of like decades.
Interesting.
So just something I was thinking of. Yeah.
Well,
Oh, thank
let me
you
see.
for
So,
sharing that. Yeah, that's excellent.
so
I
Andrew
had
just
a
popped
comment
in.
I wanted to make,
Oh,
really quick about the gravitons, because I kind of missed my chance earlier. There were these
Sure.
researchers who were doing calculations. They had calculated the minimum possible value of alpha. So, and we have known that alpha is the size of the first and largest mathematical term that you have to add to the gravity equations in order to describe the presumed quantum unit of gravity. And I thought that was interesting. This is a paper that came out last year. So just wanted to share that.
Yeah, sure. Let me make sure I understand that. So they're saying that you're going to vary alpha?
No, I
Tammy?
was saying that I had read a paper about how these researchers had calculated a minimum possible value of alpha. Okay, and roughly alpha is equal to the size of the first largest mathematical term that you have to add
Oh,
to
you're fading out,
the
Tammy.
Yeah, you're. Are you near your microphone?
Yeah, I'm here. Can you hear
Okay,
me?
yeah, I'm sorry you faded out. So the minimum value of alpha, 1 over 137, which is, an intriguing number. In fact, it
So
drove
it's
Polly to a nervous breakdown. He had to go be treated by Young.
yeah, but this is interesting. This paper, okay, where they calculated the minimum possible value of alpha. Roughly, that's the size of the first and the largest mathematical term that you have to add to the gravity equations to describe a presumed unit of gravity, to describe an interaction between two gravitons. So
Interesting.
I just thought that was
Okay,
interesting.
that is very interesting.
Oh, John, that's my other question,
that.
actually. What does your model say about gravitons? What are gravitons in the gem theory?
Well, gravitons in the gem theory are basically a collection of photons. It looks like they're a bound together group of photons, if that's possible.
Yes, that is, in fact.
It's a little abstract. Yes.
Yeah, we're looking at that actually in the lab. Are you familiar with squeezed vacuum states?
Yes, I am, to some extent.
So a squeezed vacuum state is an entangled two-photon state, and you can think of it as a composite particle
you could
with
view
spin
it
0
as
or 2.
entangled photons.
Yeah, a set of two
Graviton
entangled photons.
is a group of entangled photons, basically.
Effectively, yeah. So you have a spin state of 0 or 2, depending on how you do it, and then you have a variable vacuum noise, which corresponds to a variable refractive index, which is equivalent to space-time curvature. So same thing. And then, you carry momentum just like a photon, or more or less. And your wave equation is it comes out of the uncertainty principle, because if you have one quadrature that's squeezed, the other quadrature has to have an amplified
Interesting.
vacuum noise. Yeah.
Very interesting. We'll discuss this more. I'm trying to learn quantum mechanics better.
You gotta
than I did.
for this. You gotta.
Yeah, you gotta understand quantum mechanics, and I used the quote of Feynman that there are about 4 people who understand general relativity on the Earth, and nobody understands quantum mechanics. He says that after winning the Nobel Prize for doing quantum mechanics.
Well, we're getting closer to it. That's for sure.
True.
So anyway, the
new way of thinking.
Right. So for you, if as a plasma physicist, I might recommend looking at J.P. Vigier's work, if you're familiar.
Vigier?
Yeah, maybe. He was from Einstein.
Vigier was
from Einstein's time, but they didn't let him do
Einstein.
work
He's
in
a
the
very
US.
smart guy, and I actually got to meet. I had the pleasure of meeting him at one conference.
Nice.
And we had a brief chat, and he thought my theory was kind of interesting that it predicted G.
Right. So Einstein, he wanted to work with Vigier or Vigier. I don't know how to whatever you pronounce the last name is, but
Yeah, well,
he wanted to work with him
because I was corrected.
Yeah. So like Einstein was convinced at the time that you didn't have spooky action at a distance and stuff, and Vigier's models, his models showed they were a stochastic interpretation of quantum mechanics, and moreover, if I'm not mistaken, there's some way that these stochastic models of quantum mechanics got around Bell's inequality. So you could have a hidden variable as long as the system was chaotic nonlinear system. So the envelope, the probability envelope of that chaotic nonlinear system, a deterministic chaotic nonlinear system, was equivalent to the wave functions in the square of the wave functions in quantum mechanics, the for the observables. So basically, you can have it be deterministic, but if it's so chaotic that you can't make any better predictions than what the uncertainty principle gives you anyway, then apparently you can use those sorts of deterministic models for quantum mechanics, or that's what they were looking at, and that's why like the Research Institute for Advanced Studies and IAS as well. That's why they had so many people looking at chaos theory, complexity theory, and nonlinear dynamics, because Einstein was telling people to look at that direction but he couldn't work directly with Vigier, so he just got the best folks he could.
Why couldn't he work directly with?
Because he was a communist, and he couldn't. People wouldn't let him in the U.S.
Okay. Yeah, right. It was the Cold War.
Yeah,
and
so
it's
really unfortunate. We probably already have like a lot more tech if they had a chance to work together. But anyway, that chaotic nonlinear model will be more familiar to you if you've worked with plasma physics. So it may be a good jumping off point. So good luck to that. And if I'm not mistaken, Drew's model, your gem theory, is very compatible with what Drew's working on. So I'll let him talk now.
Yeah. So let's go to Drew now. Let me unmute.
Yes, Drew.
Unmute Drew. Drew, welcome, sir. Sorry for the delay.
Hello.
Sunny Florida.
Yeah.
How was Ida or Idalia or whatever her name was?
I don't know. I didn't bother to learn the name of that silly storm.
Oh, okay.
I feel bad for people that were in its path, but it has no effect on us on the East Coast. So.
Oh, okay. Great.
Okay.
I just wanted to just real quick give an update and one, John, your presentation was amazing. I didn't understand any of it, but
sure.
I'm going to make sure Charlie watches it just to see if there's something in there we could use. I get crazy when I don't see any physical way to create any of the stuff that you're talking about. You know, I'm a builder. So
No. Hey, Drew,
the
I
stuff
understand that. I understand that. You know, I tend to be kind of a hands-on character, so we actually suspended some coils underneath a balloon at one point, and we would turn on the power, and the balloon would rise, meaning it had gotten lighter, and then we turn it off, and it would sink. So we did try and do very straightforward experiments like that.
That's a hell of a demo. I wish you had posted it publicly. I would love to see that demo. And I'm sure everybody else here would too.
We'll figure out how to do it. We'll do it. We'll have a good show.
Okay. Well.
So Drew, your device has a diverging field. So the effect you're seeing in your propulsion device should be identical to his E cross B drift.
Yeah, we
according to plasma physics,
we just filed, I don't know, 120 more pages to our patent. Charlie's got some madness called the divergent something. I don't understand it.
He's got a theory. Good.
He's got it all explained out. The whole divergent, whatever the heck it is. It's how the whole propulsion system works. If somebody can figure out what it means, let me know, because I don't know. I watch him write these things. So yeah, it's very exciting, very, very interesting. I gotta head out.
What is your device? What does your device do, Drew?
Well, right now it's doing about 31% Earth Unity propulsion, propellantless propulsion.
Wow.
So lifting 31% of its own weight.
One of your old students, Dr. Charles Bueller. It's
Bueller?
one, yeah.
Bueller?
Yeah.
Yeah, because I taught at the University of Central Florida, UCF, for a while.
Yeah. So anyhow, basically we put in energy, get out propulsion. We just call it the Star Trek impulse engine.
Excellent.
It's working fine.
My theory says you ought to be able to build stuff like that.
And we did. It just took a while. But what I just wanted to mention real quick before I got to scoot is I was out there playing around on this space travel calculator by 9planets.org, and it's very interesting. It's free. It's a little space thing. You can put in what you want. I put in 0.3 G acceleration because that's what our propulsion system can currently do, is 0.3 G. And mass of the ship, I don't know, 45 tons or so.
Sure.
Which is about the throw weight of the big, whatever, the big SpaceX toys.
The SLS throws 42 tons out to escape velocity.
Sure. Yeah, we only need to get to Earth orbit. We can push ourselves out after that. But the cool thing is, when Mars is closest, it's about 4 days to Mars, and that's accelerating the whole way. And decelerating the other way, because we don't ever run out of fuel, we don't ever have a problem. So we're gonna be able to get to Mars in 4 days at a third G, with the ability to flush the toilets the whole way. It's kind of cool.
Great.
And when Mars is on the other side of the solar system, at whatever it is, and when it's like 155 million miles or so, it's 6.7 days to get to Mars. So we're talking about less than a week to get to Mars from pretty much anywhere it is in the solar system on any day that you want to go. So we're real excited about that. We're real excited.
That is very exciting. That is very exciting. And our trip times to Mars will continually drop. I just got a paper accepted where I can get there in 3 months. I mean, but that's using my microwave electrothermal water thing, thruster, using big solar panels. But this
sounds
3 days is much better than 3 months.
Yeah, that sounds like you're shooting high velocity steam out your butt.
That's well, yes, basically.
Yeah.
It starts out as a plasma, but it comes out when it finally expands, it just turns into steam.
Yeah. Well, we're operating at about a 30% quantum efficiency. So basically we can do about 0.3 Gs.
More power to you.
Yeah.
Drew, you need a different word for that, because quantum efficiency is used in a different context usually.
Oh, yeah, okay. Yeah, we're whatever you want to call it. We can lift about a third of our own weight right now. A little less than a third.
If you're on the moon, you'd be able to float.
Yes.
If I may, Drew, in terms of your most recent thruster adaptation, I know there's only so much that you can talk about, but from the patents that I've read, I've seen tremendous similarities between what you guys patented and what LaForge patented back in the worldwide patent papers. So he never did patent in the United States, and so you're free to do that. But I'm wondering, was this the carbon nanotubes adaptation of your nanoplate surfaces?
No, I don't know what you're talking about there.
You did in the patent. You talk about the use perhaps of carbon nanotubes.
Oh yeah, that was back when we were messing around with surfaces that had little things sticking out of it and flat plates up against it. We figured if you went all the way down to the nanoscale, you'd be able to have a forest of little antennas and little flat plates. Yeah, that was interesting. We've since evolved past that. We might go back to it, but we're working on a completely different mechanical process, a whole different design.
What do you mean by mechanical?
Well, just physical. Just we have a whole different
Are
physical
there
layout.
rotations or physically moving parts here, or is this
No,
considered?
it's all solid state. No, it's all solid state materials.
Are you able to talk about anything that would maybe just kind of enlighten the public in the general scope without violating any of the patents or NDAs?
No, about 2 weeks I will, though. 2 or 3 weeks.
Okay.
I'm looking forward to it.
Look forward to learning about it.
Stuff published.
We look forward to it.
Oh, thank you. But the last thing is, I don't actually trust this program when it starts talking about choose your universe. But if you switch over to the Einstein universe in this model and you plug in a star, which will just take something close like Barnard's star, and you plug in some numbers, it says that at 1/3 G, I can get to like Alpha Centauri in about 8.5 years. So
That's pretty
exciting.
That's nice.
It's like, I think the closest I ever get to light speed is about 0.9. So it's not a real,
Sure.
And that 8 years is Earth based. It's like 6 years ship based, or 4 years ship based, or something.
Sure.
Like that. 5 years ship based.
That's doable.
So I just thought that was interesting that with and this is little more than mechanical drive. I mean, it's like having a rocket engine that never shuts off. So it's not warp drive by any stretch of any imagination, but still the stars are within reach. I
They
personally
are.
can go anywhere in 8 years. I'm not going to take an 8-year trip anywhere, but people are crazy. They do things. There's lots of
People
that
do
would take
things
an
like
8-year
that.
trip. So,
Hey, could you make a little forest like biosphere thing, and then use the forest, like use the trees as your pegs in your system for your propulsion?
yeah, I don't know. I doubt
I
it.
say,
I don't think they would like having high voltage pass through them for.
There's electroculture. It actually improves tree growth.
Yeah, this would like vaporize tree growth.
Yeah, it depends on the voltage.
well, Drew, we're looking forward to seeing some pictures and things, some video. Get us some video of this thing.
Sure.
I mean, I'll try and get some video of the balloon experiments. We put the coil under the balloons, and anybody can do it. You just look at it, you'll see how to do it. And
are you able to tell us a little bit about the
you
coils?
turn it off, the balloon sinks because it gets heavier.
Are you able to tell us anything about the coil geometry, John?
Oh, that's the simple thing. We just took toy motors, where they have those nice little laminated rotors, laminated iron rotors, and we only use single phase power. It turns out the equations say it doesn't work as well with single phase as with 3-phase, but we use single phase power, and we got it to work. And you could see it in terms of the coil getting lighter, and the balloon pulling up to pull the little electric wires off the surface of, it was concrete floor, and then we had some very thin wires connecting the coil to the power source. We turned on the power, and
is it possible that it's due to heating? You expand the gas in the balloon?
No, we actually tied a bunch of resistors together so that it would just make pure heat, and it didn't do anything. It bobbed up and down because the heat just generated kind of vortices that hit the balloon and made it bob up and down, but it didn't go up and then drop when we turned off the power. The reaction was instant also. The bobbing motion took several minutes to actually form.
Simple experiment to try anyways. Awesome.
Yeah, it's a simple experiment. I'll show you guys a video next time, and you can do the experiment yourself.
That sounds awesome, because in this community, you basically got people
But
pounding
be
down the door
careful.
trying this.
So some people in black trench coats may show up at your door and say, we'd like to invite you out to Site 51 to continue your research. I'm just kidding.
Well, I mean, if you put it in a Faraday cage, maybe they won't find it.
There you go. There you go. So, gentlemen, I'm sorry. This is turning into my son is getting ready to move back up to Wisconsin. Believe it or not, my son, who was raised in Wisconsin, does not like Texas. So he's getting ready to move to Wisconsin. I'm living here in Texas, and I've lived all over the country. So one place is the same as the other. And anyway, I'm going to have to go help him. So are there any last questions? Then I'm going to have to, unfortunately.
No, John, but you know what? I want everyone to give you another enormous applause.
Thank
Mr.
you.
John
You do me great honor,
Brandenburg,
you
everyone.
guys. You do me great honor.
Sir, thank you so much for the presentation and the comments and the ideas and just sharing time with us today.
Okay, and I'm sorry to report to you that they have made it may have been a spacecraft an interstellar spacecraft that entered the Earth's atmosphere, burned up and made a bunch of iron globs with alloy in them. And part of that component may have been parts of a nuclear weapon. I'm sorry.
Well, if we're lucky, it was a fusion or fission reactor.
Yeah,
it could easily have been a nuclear power source. All I know is, from my work experience, they use beryllium, by the way, in the triggers for hydrogen bombs. It's the small atomic bomb that triggers the big hydrogen reaction. Those are all surrounded with beryllium because it's a good neutron reflector. They use lithium in the hydrogen part of the bomb because the lithium turns into hydrogen when irradiated with neutrons. And then they use an uranium casing around the whole thing because that boosts the explosive yield. So you can look that up on Wikipedia and look up beryllium and use of nuclear weapons, and you'll see it. I will be sending a document to Tim that he can put on the website showing that, yes, this is what is in the elemental assay of the droplets they collected near New Guinea.
And then the men in trench coats will show up because you just sent me a plan to build a bomb. So,
well, I didn't. No, there's no plan to build a bomb. They're just saying, like, if you had a spacecraft carrying nuclear weapons, then you would expect to find these elements in this. And I hate to tell everybody this because it bums them out, but we have to face up to the realities of living in a real universe.
Well, John, on that note, let me bid you a fond farewell, sir. Thank you once again, and definitely send it over, and I will get it posted.
Drew, carry on your work. Do this thing.
I have every intention
you too,
of
Michael. It. Michael, I'm going to give you a good theory for superconductivity, and you're going to be able to go in the lab and make this thing and make it work.
John, why don't you come down here and visit our lab? We'll show you what's on the drawing board.
Where do you guys sit?
About 30 miles north of the Space Center, 30 miles north of KSC.
Oh, okay, great. I'd love to visit. I used to live at KSC, basically. I lived in Cocoa Beach, near I Dream of Jeannie Lane. Yes.
Okay.
Come visit.
John, I'll take you to the studio now.
Blow your socks off.
Thank you again, sir, and have a wonderful day.
You have one, Tim, and thank you again for having this conference. This is just a wonderful conference you've been able to create.
Thank you.
Oh,
I got to go too. Thanks, Tim.
Okay. Yep. Well, thank you as well, Andrew. Sorry about the troubles.
No, it's fine. I didn't understand this was invitation only to get into this thing, so I will come earlier next time.
No, we've been going for about 4.5 hours. Guys, do you think that we should close things down for today? Yeah, I see a nod there. I see a nod. We were able to
sure.
run through Phil's gallium thing. Okay.
Well, I just had a basic question to Jeremiah.
Yeah. Well, why don't we do that, and then
Right
we'll
here.
close things down in just a few minutes.
Okay. Yeah, sorry, I did not write down the flow meter you were talking about earlier, but how do you call it?
Oh, it's not a full flow meter. This is something that I built myself.
Oh,
And it just measures the displacement against the spring constant. So it's using a fiberglass rod, which is not going to interact or cool down the gallium or anything else that has a very tight transition temperature. But I'd recommend using that as a material in comparison to a heated rod, because then you won't be dealing with the cooling effects or the conductivity of the material. And it just happens to be a very easy solution.
yeah, definitely. Can I can I buy you a fiberglass rod or anything? Or?
If you're asking for a pre-built meter, then that's something I suppose I should probably put together. Actually, I'll mention this too. Myself and a bunch of the best researchers that I know that I work with, mainly the engineering types, we've been talking about starting a small website to sell specialty meters, things like time differential measurements and or what we call T-field meters, things that will detect direct scalar potentials from isolated sources, and that can measure in a direct way the change in velocity c in a localized environment. So we think that these meters are needed, and there's no place to buy them right now. In fact, there's no instructions even to build them, except for the few outlier pieces of information we can find on the web. So we want to sell these things, and we want to really get them out there for researchers like you and I and the many other people that are working on this in our small community. It would be tremendously beneficial if we could just make easy measurements.
Yeah,
And that's something we are going to be working on. So yeah, when we get that all figured out, and it might be a bit too long for the time frame of your experiments because you have currently other contracts. So I'll tell you what we are going to do, and you can build it yourself. But otherwise, yeah, if you don't mind waiting, we'll be able to send you one of these things for free, and it would tremendously help.
Yeah, definitely. Well, I'll pay for it, obviously, because it's not free on your end either. But so yeah, just let me know. I think you have my email address, so just let me know anytime, and I'll purchase it. Thanks a lot.
Yeah, absolutely. The same concern that you have is the same concern that we've dealt with. There's really no good way to measure a lot of these types of effects, and there needs to be a source for this type of specialized equipment.
Yeah, I don't really believe in reinventing the wheel. So since you've been through that already, then I'll just
I'll send you
take
one.
advantage of it.
As soon as we get it all figured out and we get good stable measurements, the only thing we don't have on our team yet is a good programmer. And a lot of these measurements would be much better if they were displayed directly on, say, a Arduino based LCD display instead of the current system which we're using, which is a direct connection by BNC cable to an oscilloscope. So
Okay, I'm a good C++ programmer for these embedded devices. I can write GUI using Qt also. I had the Arduino, but I gave it away to my buddy. But yeah, over time I could definitely help you out. Maybe we can do like an exchange of services.
oh yeah, absolutely. And then also Michael Perrone mentioned the other day, which I did not know, he was a pretty good programmer. So he's offered his help, and we know that guy's a genius already. So
Yeah,
I think a lot of these things can be done. It's just not, it's a matter of time. You know, we're really bouncing against the clock here and trying to get these things done. And we have so many projects going on right now.
Yeah.
But Jeremiah, you are no slouch either, my friend. Although you have been hiding out recently.
I do hide, but I certainly stay busy. Though I always kick myself in the side because I think that there's always more that I could get done than the amount that I actually do get done. And I guess that's just one of those things. It's got to be motivation. So I should be doing more than I'm currently accomplishing, and I run into a lot of shortfalls. Most of them are my fault.
Yeah, you're very active on Bernie's channel also.
Well, he does offer an open forum to talk about these things, and even if the shows are sometimes ridiculous and filled with woo-woo and other weird things, like it's a great open format with a small audience where we can really engage. On these larger channels, we can't engage. That's the problem.
Yeah, that's true. It's more
Well, it's community based, right? It's
Yeah.
we're trying to do the whole community, so to speak.
Yeah. All right. So yeah, thanks a lot, Jeremiah, and thanks for your help, man. I'll just find a name for your company, and I'll do promotion for your company right away.
Yeah, we're taking suggestions for a name. We have not determined one yet.
Yeah.
But what would you call a company that offers super weird and exotic measurement equipment? I have no idea what to call it yet, but I'm sure we'll figure it out, or somebody like yourself will suggest a great name.
Yeah, I'll try to find something, and I'll send you some suggestions.
Yeah, I also do have a few lab updates. Unfortunately, I'm going to have to do them one picture at a time. StreamYard is not allowing me to share my quick view, which means I've got to load one image at a time, then close it, then reopen another one. But I do have one, and it's about the invisible wall machine based on the 3M.
Do you want to put that up, or do you want me to put that up, Jeremiah?
Yeah, let's just pop that up real quick, and I'll briefly mention it. So what we're looking at here is 4 rollers that have not been machined down yet. These have got to be rounded off at the edges, and they'll each be suspended from a nylon bolt that passes through the center. It's a 10 millimeter wide borehole for the bearings. And on both sides, there will be a either acrylic or Lexan structure with a 4-inch by 4-inch wide square window. So we're going to charge the living hell out of this belt. I'm considered using treble electrics like a Van de Graaff generator, but it's more than likely I will just simply inject the charge directly on the surface of this belt. And so this is a really simplified case of the 3M invisible wall. We know that we need to reach 1,000 meters per second, or excuse me, 1,000 feet per second, as in the original case that David S. had reported. And I've got another buddy, Andy Smith, who you've done a great interview with, Tim. And he was actually there within 1 week of that same time that Swanstrom was there and witnessed this fantastic event where his electrostatic voltmeter had detected over 1 megavolt of potential at some 20 feet distance. So the 3M invisible wall, for people who aren't familiar with it, this was created by the separation from a polypropylene large roller going through a slitting machine, and it had several million volts on it. And he reported that things like small insects and even birds would get stuck in this field if they flew in from the outside because they had a large bay door open. And it only happened when the humidity was extremely high. So in some of the official reports that have been misinterpreted, it was said that the humidity was preventing this effect, but it turns out that based on our test, the humidity was actually the catalyst. And it seems like the individual conductive molecules of dihydrogen monoxide, H2O, were getting wrapped up in this electrostatic flux and circulated around in place. So we think that humidity is extremely important for producing this effect. And all that we need to do is basically constrain that. So once we inject the humidity in from an ultrasonic source, we should be able to create the same type of phenomena on a very small scale. And finally, we can explore this idea of force fields and open bay doors to the vacuum of space, as we've already seen work with plasma dynamics, because this test was done, some of these tests were done years ago. Plasma dynamics show that we can create a significant pressure differential between side A and side B using a plasma window, as they described. And this would effectively create the same phenomena, and we can explain this all using Richard Van Dyrek's mathematics. Even though they may have errors, they do prove out in the lab to be true, or at least functional enough.
Nice. So you have your version of the force field. I have mine also, but based on time potential lasers. So you just alter the time of a laser. I mean, any weapons. So it's gonna the projectile is gonna stop right away. Nothing can go through. So, by the way, I already have an idea for your name. Maybe Doc Brown. Doc Brown in Back to the Future.
Absolutely.
Yeah.
Probably one of my favorite characters from film, to be honest.
Yeah, definitely. Yeah, that would rock. Yeah.
And then I've got one more I'll mention too, because I know a lot of the viewers that are looking at this presentation today are also quite familiar with Bob Greenyer's work. So let me go ahead and open this other file up. Man, I wish I could just simply share this whole thing unobstructed, but it doesn't want to comply with me today, and I'll just have to deal with that. So let me go ahead and hit present, share screen, And then we should be able to get, here we go. So this is a very different bagel coil from what we've seen on Bob Greener's channel. And I've presented this as well simultaneously on Jeremy's channel and also on Bernie's channel. And
So
what we're
sorry,
looking-
I can't see anything.
Okay, so we just got to get this loaded up. It's sitting there waiting for anybody to full screen this. That will be on you, Tim. I just launched it. And I can see it.
Yeah,
There we go.
All right, cool.
So this is a 14 by 14 by 14 tor. The largest tor is the full ring that creates this large circle. The second tor is each individual loop of these many winds around that core, and the third tor is the individual windings at the edge of the wire. So we have basically 3 layers of a 14 by 14 by 14 fractal, and inside there are a total of 8 wires creating 16 connections, as we can see in this brascence here. The reason for why we think this is going to be significant is each one of these layers will stack epsilon on mu in an alternating manner. So each time we have a general single conductor producing an electromagnetic field, we would have epsilon at 90 degrees to mu. And they would be completely photonic, and they would be in compliance with our general net energy equivalence. But in this case, what we're doing is we're actually aligning at 0 degrees epsilon on mu per layer, so down to the 8th layer with these parallel fields. What we're effectively doing is compressing our localized space-time. And we'll be checking for the velocity of the center conductor's ability to transfer charge from one side to the other and the signal path length. We do believe that with this device, we will be able to slow down the local velocity c at that final 8th layer of the center conductor. And this would be very, very fundamental, because what it tells us is instead of the high energy warp drive physics that Alcubierre states, this would be much more like the Eric Lentz warp drive, where we're basically using low energy, but we're using nested fields that are self-interacting in a phase-conjugated way. And we don't think it's that complicated, really. It should be pretty simple. This wire practically winds itself, and I built a special machine just to make this wire, which made this very easy to assemble. Much easier, in fact, than anything we've tried before. So this is replicatable.
Nice.
Amazing.
Hey, Jeremiah, are you got those windings in series, or are you feeding it power in series?
I'm sorry, Mike, but you were very, very quiet in the background. I could not hear you.
I think he was asking if you were winding it in series or.
Oh yeah, we're gonna stack them in series. They have to be the correct direction. So we're gonna go with a continuous right-hand rotation all the way around, and then we're just gonna stack those fields on top of each other, and then finally measure the total change. So we'll go 7 layers stacked, and then we'll leave that 8th layer, the final single conductor that goes through the center of the copper on copper core. And I want to also point out this is a coreless coil in terms of any ferromagnetic elements. So technically it does have a core. It's all made of copper. Everything here is copper. And so, any effects that we get, they're not going to be caused by ferromagnetic phase delay, but this would be an entirely lens-based system.
Okay. Well, so we got about 8 minutes left. Jeremiah, you said you had a couple other pictures too, right? You have 2 more?
I do. And once again, I'll have to stop this screen share, and then I'll have to pull these up.
Yeah, let's run through those, and then we'll close things down. And again, I want to thank you guys for so much for showing up today and participating and showing us all of this remarkable technology.
Yeah, thanks, Tim, for all the contacts. Also, I'll pay back as soon as I can get some revenue. Really appreciate it.
So there's one more.
Oh, here it is. Okay, sorry, I'm spacing out a little bit.
All right, so this is just an up close of the wire, in case people were wondering what it actually looks like. It is a single solid copper core of the same gauge as the wire that's wrapped around it, and the winding machine that we constructed will wrap this external conductor around that same. So we have an orthogonal field that's being produced every time we pass current through both wires. And I'm going to go ahead and stop that share, and then we'll go on to the next.
Wonderful. Yeah, thank you.
And then this is another thing here that I'm about to pull. It's an experimental coil, and we don't know what the results are going to be yet because there was a break in the wire. And actually, you can kind of see that in the picture on the left side. But this coil is wrapped around a ferrite core, which is technically two magnets with the north poles superglued together. And very much like the Manellis device, or like the Norman Wooten magnetic field modulation device, we can potentially apply this same field effect where we are modifying one of the two variables that control the refractive index through the second conductor, which is responsible for carrying the current loop in the core. And we think that we can affect the Brownian motion of the ambient environment and the motion of the thermal energy, both within the magnet and within the wire, by modifying both factors at the same time. So we're hoping to extract just a little extra energy out of this. We don't expect a COP greater than 1, but we do expect a COP significantly greater than what could be achieved sheerly based on the transformer metrics.
What's the Brownian effect again?
The Brownian effect would state that any random Brownian motion from thermodynamic energy would be randomized in a flat space-time or in any kind of space-time curvature that is generally uniform. But in this case, we're attempting to modify the uniformity of the space-time curvature by applying an additional current from the wrapping around each center conductor. And we expect that we could use that time delay or that slowing down of the local velocity c to add the thermionic motion into the system cyclically.
Okay, I see. So that's gonna alter, like you said, that alters the speed of light.
That's what we're hoping for. It has not been tested yet, and my confidence is not incredibly high about this particular iteration of the device, but it's fairly high about the triple Tor coil. We've already seen similar effects with other coil configurations, and so we expect that one to work, but this one we don't know yet. Here we have to modulate the direct domain orientation within the two ferrite magnets.
Okay, can you stack them up together to amplify the effect or something like that?
It's been theorized by one of our group members that we could stack these, but we haven't even gotten to that point yet.
Okay, interesting.
Wonderful. Well, Jeremiah, thank you so much. So guys, I think with that, I think we're going to close things down. Mike, I know that you're looking at some stuff, but I probably don't want to get into that. I don't want to start something that's going to take us too far into the next hour. So why don't we close things down for today? Let me thank everyone for attending. It has been amazing having you guys here. And I think things went very well. Started out kind of slow. I think Burning Man kind of slowed us down a little bit. But thank you to everyone. And thank you to everyone watching APEC. We have another one coming up. I believe it's September 30th. And then we have another one in October. And then we have those open mic sessions too. And those are every staggered every 2 weeks. So we got lots of stuff going on. So,
and if I may, one final request, Tim. And once again, thank you so much for being the best host that anybody could ever ask for. If you wouldn't mind posting that final open chat invite link now that we're in the after show for anyone who wants to join off air. And if you wouldn't mind passing host to me, if that's something that you can do on your end, I would be glad to, cover a couple other questions and bring people in who just don't want to go public. So let's go ahead and do that and finish this up. It was a fantastic show, and I'm so glad with how things went.
Okay, so let me do that. StreamYard presentation link.
You
so
guys
I'm going
like
to send over.
Circuits, I like to show you something.
Okay. Guys, I'm going to close things down. It has been wonderful.